Time for a pop quiz. Problem solved.
Look at me! Why did you even rope me into this? Because he roped me into this! Well, him over there, he roped me into this! Well, he roped me into this!
Hi everyone, welcome on in. My name is Penn Center. Hello 30. Hello Rex. How are you doing? Happy whatever day it is. Is it Saturday? Happy Saturday. Or Sunday for some of you. 2 a.m. Oh my god. Don't worry, the next presentation is in Slender's time zone, so it should be a little bit easier for you to attend. It's going to be like 8 o'clock in the morning for me. Itchy legs, damn. Alrighty, I'm gonna go ahead and get some stuff set up over in the mathematics Discord server, so hang tight. Hi everybody, welcome in. We're just about to get started for the third presentation for real analysis. So if you haven't done so already, feel free to DM me. I can get you into the roles, into those channels after today's presentation if that's something that you're looking at doing. Hello Riemann Zeta Prime. Discord calls me by dirty. And hello in Discord. Yeah, welcome in Riemann Zeta. All right, let me open up that Discord chat as well. Let's see if I can monitor that as well. Hello, Aha. Welcome in. Is this the third? Yeah, so this is going to be the third presentation in the series. The first presentation was done by McKenna and myself. We talked a little bit about sets and proofs and things like that. The second presentation, that was done by Dingus, and we talked a little bit about sequential limits and some of the results that come from sequential limits. And the third presentation today, we're going to go into a little bit more on some proof techniques and cover a little bit more of the kind of set theoretical stuff, as well as, if I can get into it, some more of the sequential, some of the properties, I guess, that come from some of these, the definition of sequential limits. Hi, chat. Hello, this is my first time. Welcome in. Oh my gosh. Pedro, nice to see you. Welcome in. All right, so happy Saturday, everyone. My name's Brian. We're going to be talking a little bit about what's going on with real analysis. So we have a new presentation today. I want to talk a little bit, so for those of you that might be interested in giving a future presentation here in the server, I want to give you some information about how you can do that. For those of you that are not a part of the real analysis reading group or the presentations, feel free to DM me. Like I said, we can get you into the roles that you're going to need in the mathematical Discord server. And I can do that after the presentation's done. So kind of the goal for today is to talk a little bit more about some of the, I guess, definitions that we're going to need from sets. So looking at set difference, complement, Cartesian product, power sets. We're going to talk a little bit more about some of the proof techniques that we can use as we start to work on some of the problems that are posted in the reading group. So specifically, we'll take a look at how to negate statements, how to set up a contrapositive and contradiction kind of proof. And then kind of the main sections that we're hoping to cover today, the big one is cardinality. So we want to talk about cardinality of sets, countability of sets, and discuss a little bit about Cantor's theorem. So that's kind of the first big push of the day. And then if we have enough time, and I'm not boring everybody, we'll go on to talk a little bit about sequences afterwards. So I don't know why Cauchy sequences is up there twice, but we're only going to discuss it once. So we'll talk a little bit about the Monotone Convergence Theorem, the Bolzano-Weierstrass Theorem, and what a Cauchy sequence is, and talk a little bit about the Cauchy Criterion. Hi, Beard Hero. Welcome in on Twitch. Hope you're doing well today. When are we doing measure theory as part of analysis? Get out of here. Hi, Solomon. Welcome in. This is your first time joining. Fantastic. Okay, so if you're interested in presenting for the real analysis reading group, feel free to DM me and just tell me that you're interested in making a presentation for us here in the mathematics server. We are mostly through the topics that we need to talk about the derivative calculus part of real analysis. So what we're really going to be working towards is trying to find some folks who are comfortable talking about infinite series. So if anyone has some background knowledge in series, convergence of series, Riemann integration, or any of kind of the things surrounding integration, as well as the fundamental theorem of calculus, and you're interested in presenting on one of those topics in the future, that's going to be probably closer to, we're going to be into March, I think, by the time that we're doing those presentations, so we're about a month away. But if you're interested in any of those, just feel free to send me a DM. So I'm happy to give you references. We're using Abbott Understanding Analysis. This is my very old ancient version of the text. But I'm happy to supply you with resources for the reading group. And then I myself, Penn Center, as a department chair here in Canada, I'm happy to provide a short academic reference for presenters that that I think are quite excellent. So I'm really happy to do that if that's something that would help motivate you, I guess, to join the group. Hi, Matt Spellbook. Hi, Cookie Bite. Welcome in on Twitch. Hope you're doing well. So let's first start talking a little bit about sets. So we'll do a little bit of a review here and then add in some of the new items or the new definitions that we're going to need to do some work. So the last time that I had presented with McKenna, we talked a little bit about mathematical statements. And so when we talk about a statement, we're really thinking about something that's either true or false. So it has this like natural dichotomy to it. And we also took a look at conditional statements. These are any statement of the form if P then Q. And we usually call P the hypothesis, and we usually call Q the conclusion. Now, we want to talk a lot about these conditional kinds of statements because these are the things that we want to prove. So for a lot of students, real analysis is the first time that we really get to kind of play around with proofs. And analysis also adds in these really interesting things called quantifiers. These are phrases that refer to specific elements inside the set. So we have these universal quantifiers where we're looking at a set and we're describing a property that everything in the set has. So that's a universal quantifier. And then if I'm looking at a set and one or more of the objects inside the set has a property, then we describe that using an existential quantifier. So we'll see a little bit about how these things kind of tie in with some of the proofs today.
He roped me into this. Well, that one over there roped me into this.
Hi, Famish. Welcome in. Like my hexaflexagons? Yeah, they're nice, eh? So the basic proof setup we talked about the first time that we got together was if I want to prove a conditional statement, I basically have to assume that the hypothesis is true and kind of lead myself through a series of mathematical adventures to get to the conclusion. And we looked a little bit about how to work with quantifiers inside a conditional statement as well. And if I have a conditional statement involving a universal quantifier in the hypothesis, so I'm saying like if for all something happens, we usually use the choose method. So we just kind of pick one of the elements inside that set and then kind of move forward with our mathematical proof. And if I have an existential quantifier in the hypothesis, we usually start by constructing the thing that we want. So if I see a statement like, if there exists an object that has a property, right, then I'm actually trying to construct that object and then show that that object that I've constructed does the thing that I want it to do. So I often refer to these as the choose method and the construction method. And if you want to have a little bit of a deeper look at what those looks like, you can kind of take a look at the first set of the slides. With regards to sets, we talked a little bit about set. A set is a collection of objects. These objects are called elements. And then if all of the elements in a set are also a part of, at least as big of a set or a larger set, we call it a subset. So here are a couple examples here. In the example here on the left, we could say that A is a proper subset, so there's no equal sign underneath that little fancy C symbol. So here A is the set of elements 1, 2, 4. It's naturally contained inside of set B. Set B contains all of the numbers from 1 to 5. Looking at the right-hand side, P is the set 1, 3, 4. I noticed that 1's not a part of Q, so we wouldn't say that P is a proper subset, or P wouldn't even be a subset of Q because 1 is not an element inside of Q. This is Rizthor and the goat is back. Yeah, okay, thanks. I appreciate it. We also talked a little bit about unions and intersections and what those things look
results.
like. Peak and Flow, thank you very much for the tier 1 subscription over on Twitch. Much appreciated. And Discord gets to see the beautiful emote firework. So if I'm looking at the left side picture here, I'm looking at A and B. And I'm looking at something called the union. I'm looking at the collection of all of the things inside of A and B. So I'm looking kind of over here right now on the left side. Now in this case, A is completely contained inside of B, so the union of A and B is just B, which is 1 to 5. Cookie Bait, thank you very much for the follow. And then with our picture over here on the right, the intersection is the list of shared elements between two sets. So in this case, I've highlighted in light blue here. Well, the picture that I've taken is highlighted in light blue what the intersection looks like. So in this case, 3 and 4 are the shared elements between P and Q, so they would be naturally a part of the intersection here. And then kind of the last thing that I want to talk about with regards to just some of the review that we talked about in the first lesson was this idea of setting up functions or maps between sets, and specifically injective, surjective, and bijective kinds of functions. So if I have a function that goes from set A to set B, I call it injective, and some of you may also know this as 1 to 1. So it's injective if for every x and y inside that first set, you have that f evaluated at x equals to f evaluated at y implies that x and y have to be the same element. So we're looking at two pieces in the output space, and we're saying, okay, well, if these things are equal, if this was a 1-to-1 function or an injective function, when I pull that back to set A, those things are actually end up being the same, right? So if they're equal in set B, when I pull it back into set A, they're also going to be equal. So that's the idea of 1-to-1-ness. And we also have this idea of surjectivity. This means onto. So in other words, every possible element in the space B comes from an element inside of space A. So we say that for all y in B, so for every element in that secondary space, there exists some x in A, so there exists some element in A, such that I can kind of connect these together with the function mapping f. Right, so there's a couple different examples here of functions. So injective, you can see here A and B, right? So every single one of these blue dots here in A gets mapped really nicely in a one-to-one way to these elements over here in B. Notice that not every single element has to get landed on. So this particular map is injective, but it's not surjective because not every element in B comes from a blue dot over in A. Now if I move over, this is surjective, so every single element of B gets landed on by our function mapping, right? It comes from some kind of blue dot, but it's not one-to-one. So there's a, let's see, this one down here. There are two elements in A that get mapped to this particular element in B. Right, so it's not a one-to-one kind of thing. And then bijections are the nicest kinds of things, but they're also really challenging to set up. But a bijective function is something that's one-to-one and onto, so it has all the really nice properties that we need, for example, to find an inverse or something like that. Yeah, thanks, Math. Yeah, it's the visual helps explain the difference. Yeah, that's kind of, I really like this visual as well. Credit to Math is fun. Yeah, I know. The credit sheet. I'll have to put the credits on for you guys. Peter's saying, wait, what do you mean? Is it normal that a 7th grader starts doing, what, 3rd degree algebra? Oh my, I don't even know what that means. Okay, so now we get to move into some of the new stuff. What's 3rd degree algebra? Is that like 3rd degree burns? So we want to talk a little bit about negation today, and negation has this really nice kind of counterpart with regards to sets called the complement. So the complement of a set, I'm going to use this kind of like neg A. So we're going to use this to talk about the complement of a set, and it's the collection of all elements that's not in A. And then another thing that might be helpful for us to know is something called the set difference of A and B. And we usually use this as like an A/B. I've also seen it written A minus B, but I think that's a bit of an older notation. And this particular set is all of the elements that are in A, but aren't in B. Right, so kind of written in a set builder way, it looks like this. So the negation of A, we can think about it as anything that might be in kind of the universal set that I'm working with. I'm going to take all those elements, and then I'm going to remove any elements that are inside of A. So it's all of the x's in our universal set that are not inside of A. And then the set difference, A/B, is all of the x's that are in A, but not in B. So if you want to see this as kind of like a little picture or something like that, let's say, like A. And if I have some maybe kind of bounding box like this, and this is my universal set, so all of this stuff out here would be not A. And then there's a couple different ways that A and B could interact. I mean, they could be disjoint, or they could have some kind of overlap. So let's say we have two sets A and B, and I'm looking for A not B. So the set difference is A not B. That would be all of this stuff up here. So everything that's in A, but not in B. So this is A not B, is how I always say it. Now, down here, if B happens to be a subset inside of A, then A not B would be everything except for those elements that are inside of B. What, you don't like my abbreviation? How dare you? What is mathematics if we can't have a little fun, guys? Come on. So we got Cuddler saying, a little confused on, what is this? A little confused on the surjective stuff. Does that mean that, so if we think about functions, so the question is, does that mean that f of x equals x squared is surjective? Oh, okay. So we can take a look at a function example if you'd like as well. We can do that. All right, so here's our parabola.
Oh, yeah? Prepare to be iterated.
So there's a couple, we have to probably make a little bit of a caveat here. It is going to depend a little bit on what your first set is and what your second set is. So kind of from the perspective of thinking about kind of set-to-set functions, what if we take, for example, let's see, let me move this a little bit, and we can just kind of grab the picture and play around with the picture a little bit. So here's our x squared. So what do you guys think? Do you guys think that this is injective? Is it one-to-one? Is it onto? Is it surjective? Is it bijective? What do we think? We just started, Virtue. Don't worry. Zach Sparrow, welcome in on Twitch, man. Good to see you. Yeah, so remember that surjective means that...
take my money.
Surjective means that I need to look at the output space and make sure that everything inside the output space gets mapped to. So if we're thinking about something like x squared, there's all this stuff down here that would never get mapped to by x squared because x squared is always greater than or equal to 0. So if I were to define, like if I define this function to go from the set of real numbers to the set of real numbers, then I can always find some value down here that I can never get as a part of my output space, right? So for example, I don't know, like -1, right? I could pick -1, and there's no way that I can map a real number to -1 because x squared is always positive. So this couldn't be surjective, right? So if I define the function this way, it's not surjective. But Jeff made a good point on Twitch, saying that if we restrict this secondary domain a little bit, then maybe we might have a hope. So maybe we could do something like all real numbers, and let's pop that into an interval like this, right? And we take the same function. So now I don't have to worry about this problem down here, right? This was a problem before, but now I don't have to worry about any of that. I really just have to worry about all of the output values that are 0 or positive. So now I have something that is surjective. So hopefully that helps kind of clarify the original question a little bit there. So it's going to be a little dependent in this case, because we're working with a function, on what we consider the domain and range to be for the function that we're working with. So this is kind of how I think about surjectivity.
Dear man, why don't you solve your own problems?
If your domain was complex, would it be surjective? Oh gosh, you're making me think a little bit now. If the domain was all complex numbers, could we land on every possible complex number? So you're thinking about C to C? You're thinking about C to C in a real analysis course? How dare you? I think that we're probably okay, right? Isn't the square root function... I mean, we know how to define the square root function for complex numbers, right? It's going to be a double-branched kind of function. I think we'd be okay. I think we could always take the square root of z, and we know that those things exist. Yeah, I think we'd be okay. So anyway, we don't think about complex functions because this is real analysis, my friends. But that was a fun little caveat, a little side adventure. All right, so here's a couple examples for you. Let's grab these and do a little bit of work. Let's make sure you really understand the idea of set difference and complement. So here's our first example. Let's say we have set A. Set A is all of the x's in the natural numbers. By the way, we're taking the natural numbers not to start at 0, by the way. Because we're mathematicians and not computer scientists. So we want all the natural numbers that lie between 0 and 3. And then B, set B is going to be all of the real numbers between 0 and 3. What does A not B look like, and what does B not A look like? Just spread misinformation. What? Yeah, Jeff is asking a bit more about the complex stuff. Let's save the complex stuff for when complex analysis starts, my friends. So, how do we want to tackle something like this? Well, we want to try to take a look at what A looks like. So A, I think we can just write this down. Right? I want x to be bounded between 0 and 3, not inclusive. So A, I think, is just 1 and 2, right? Now B is a little bit harder to work with, but it's basically going to be the open set from 0 to 3. Right? It's not going to include those two endpoints, so in North America we write these rounded brackets to denote that it's an open kind of set along the real numbers. So what would A not B look like? So what's A not B? So if I take all of the things in A and I remove any of those elements that might be in B, what are we left over with? The suit sidekick is not here to censor us. True. You are right, Jeff. 1 and 2 are inside of B, so technically this is an empty set, right? So I start with the elements in A, but I know that 1 and 2, it's inside B, so when I remove those elements, I get the empty set. Now, what if we look at B, not A? What's that going to look like? Dolby Vision of Penn Center, oh my gosh. Yeah, so what if we take this open set on the real number line from 0 to 3 and we remove A? Yeah, we're going to get something with 2 holes. You're right, Rex. So how could we write that? I guess if we wanted to write it in kind of a typical calculus way, we might write it something like this. We might kind of go from 0 to 1. We're going to skip over 1, go from 1 to 2, skip over 2, and then go up to 3. So we'd end up with like a number line that has these kind of holes. We get a holy number line. Right, because we've started with that full interval, we've removed those 2 points at 1 and 2, and that's what we're left over with. So now that we have access to the set difference, we could also give a definition of the irrational numbers if we wanted to, using a set difference. So if I wanted to define the set of irrational numbers, I could say that they are just the real numbers. Take away what? Define the irrational numbers, please. Yeah, we could just define them as a factor group, yeah. So our factor key. I got some fun proofs coming up for you with regards to the rational numbers. Yeah, so the rational numbers are usually defined in a set theoretic kind of way as ordered pairs, right? A Cartesian product. What is R? R is the set of all real numbers, and Q is the set of rationals. So that's one way where how we could describe the irrational numbers. We could describe it as a set difference if we wanted to. Define the transcendental numbers right now. That's homework. Oh no. Oh no. Okay, so we know the set difference is all of the stuff in A but not in B, so it might make sense here that this theorem, it feels kind of intuitive. The set difference between A and B is actually equivalent to A intersect not B. So let's just kind of go through this proof. This is a very kind of set, a standard way to think about equalities of sets. So we're going to assume that we're working on one side of the equation, try to show that it's a part of the other side, and vice versa. So let's look at the subset. So let's look at A, the set difference of A and B being contained in A intersect not B. So let's grab something in A, the set difference of A and B. So we'll just take one element in there. And then by the definition, that means that X should be in A and X should not be in B. And then by definition, if X is not in B, that means that X is in the negation of B. So altogether, we have that X is in A and X is in the negation of B. And we know that we can combine that kind of statement together in terms of an intersection. All right, so we know that if we start on the left-hand side here with an element over there, it really should be in the set over on the right-hand side as well. And then we can kind of reverse this process and see what happens if we start in A intersect not B. We can try to show that that element would also live inside of the set difference of A and B, and the argument's pretty similar, right? So we're going to use the definition of intersection and write it as X is in A and X is in the negation of B. And then you just note that if X is in the negation of B, that means X is not in B, and then you have what you need to get the set difference. So X is in A and X is not in B, and that's your definition of the set difference. All right, so we basically have shown that the elements in the right-hand side are inside the left-hand side and vice versa. So these two sets must be equal as sets. Why are we skipping the quotient sets? It's set difference, man. It's set difference. Something else, in case you haven't heard of it before, the Cartesian product. So this is, if I take two sets, A and B, I can define the set of ordered two tuples. So the Cartesian product of A and B is going to be this set of two tuples, where X is in A and Y is in B. So I take the first element always lives inside of the first set, and Y always lives inside of that second set. And you could theoretically put as many of these Cartesian products together as you want to get ordered n tuples to work with as well. So I think all I really need are ordered two tuples, and this might hopefully appease the aha gods with regards to thinking about the rational numbers. So when we go to start doing some of our proofs, I'm going to think about the rational numbers as a Cartesian product. So if you've never worked with the Cartesian product before, it's kind of like creating like an array of things. So if you were to kind of take elements in set B, I have over here on the left-hand side, and elements in set A on the top, then all I really need to do when I'm forming the Cartesian product is just to kind of list that element of A here as the first component, right? So the 2 is the first component, 3 is the first component, and then in the rows, I have X as the second component, or Y as the second component. So the collection of all 6 of these things is going to be what we call the Cartesian product of A and B. So it's a set of all of these possible ordered pairs that we can make from the elements that are inside of A and inside of B. You gotta talk about modules in chat? Oh my god. So Turdies, hi fam, how are you doing? Welcome on in. So a Cartesian product is the set of all ordered pairs between every elements. Of every elements? Oh, between every elements of A and B. Yes, that's correct. Yeah, so every possible ordered pair that we could build would be in the Cartesian product as a set. So let's take a look at a couple examples here, just to make sure you're happy with these. So let's suppose we had 2 sets. A is -1, 0, and 2, and B is a set containing the words mom and dad. What does A Cartesian product B look like? What does that look like? Who can give me an ordered pair in the Cartesian product? Jeff says -1 comma dad because he went out for cigarettes. True. -1 mom, yes. Cuddler, absolutely. -1 mom. So those are two elements in the Cartesian product, and then we kind of keep building these pairs. So the next one we could say like 0 dad, 0 mom. And if we want to be super inclusive, 2 moms or 2 dads. 2 dad, 90s sitcom. It does kind of sound like a 90s sitcom, doesn't it? Cancel this and just do algebra? I haven't thought about modules in forever. So there you go. In this particular case, we get 6 elements inside of the Cartesian product. That hopefully shouldn't be a surprise. Because if we look at how many elements are inside of A, there's 3. And if I match them up with all of the elements inside of B, I get like 3 times 2. So I should get 6 different possibilities for those of you that are good at counting. Now, how do I think about ordered pairs in the XY plane? So like every time that I'm doing like stuff from high school, right? Like maybe I have like the point 1 comma 3 or something. That's an ordered pair, right? The X always comes first, the Y always comes second. So I'm working with the XY plane. How do I think about numbers in the XY plane, these ordered pairs in the XY plane, as a Cartesian product? What kind of Cartesian product are we actually working with? Sacrifice parents for the Cartesian product? Yes. Yeah, nice, Cuddler, exactly. So what we have is, what we're doing really is kind of thinking about this as R, right? This is our X component, and then we're thinking about adjoining to that a Y component as well. Yeah, so our Cartesian product with R, these are all of our ordered pairs, where X and Y are real numbers. So there you go. So in case you're wondering, it's called the Cartesian plane, probably because it's a Cartesian product of R and R. Yeah, or R squared. R squared is another nice way to put it as well. Yeah, you can write it as R. I've seen that notation quite a bit, as R squared. Fancy, so fancy. All right, I think this is the last kind of big definition that we need today. I want to talk about power set. Power set, we use this fancy kind of like math cal P to denote the power set, and it's just the set of all possible subsets. So the set of all possible subsets of whatever set we're working with. So as an example here, if I look at set A contains the elements X, Y, and Z. The power set is the set of all possible subsets that I can make. So the ones that tend to get overlooked are the empty subset, or the empty set, as well as the full set itself. So, and then I basically need everything else in between. So I start with the empty set. I could have any of the singletons, X, Y, or Z, as a subset of A. I could have any pairs of elements, so X, Y, X, Z, and Y, Z. Or I could take the full set itself. That is technically a subset of A. So that's why X, Y, Z is here too. So how many do we have? So we started with 3 elements, and we got 1, 2, 3, 4, 5, 6, 7, 8 elements all together in what we call the power set of A. Now, in case you're curious about what this visual is over here, this visual is just arrows pointing to inclusions. So it's just a nice way to kind of organize your thoughts for some of these smaller sets. Arrows are just pointing in the direction of subset inclusion. What do you mean? Could I show 2 to the n equals r? What? Is that true? Yeah, exactly. So each path there shows what we call like a subset inclusion. So if I start with the empty set is a subset of all of these sets, right? And specifically, it's a subset of the set X, it's a subset of this set Y, and it's a subset of this set Z. Now, if I look at the set Z, it's a subset of YZ, and it's a subset of XZ, as sets that have two elements. And then, of course, XZ and YZ are subsets of XYZ as well. So it's just kind of a nice little lattice structure to help you visualize how we might construct the power set. Yeah, lattice diagram. Yeah, exactly. So it's a nice way to just kind of visualize that relationship. All right, so let's look at some of the other definitions from the proofy side of things that we're going to need here to move forward today. So if I have a statement, I can negate that statement. I'm just going to use the same symbol here to make things easy. I'm just going to call it not P, or the negation of P. And it's really just as simple as adding the word not in an appropriate place, usually. Sometimes there's a little bit of fandangling that you need to do. But for the most part, for simple statements, that's the easiest way to do this. So maybe you can tell me, if my statement is x plus 2 is equal to 5, how would I negate that? What makes sense to you? Cantor's isomorphism theorem is what you meant when we said we were doing Cantor's. Cantor's theorem is the one that says the power set has strictly larger cardinality than the cardinality of the set. So Rex on Twitch, you are correct. Yeah, so the negation is going to be taking this sentence that we have, x plus 2 is equal to 5, and adding the word not in there. So we're going to make it x plus 2 is not equal to 5. So that's this. If we have a simple statement, that's the easiest way to negate it. Yeah, Blob, you got it. Oh, Cantor-Bendixson. I don't know the Cantor-Bendixson theorem. I'm more of an algebraist, no sign. It's like reversing an equality. Yeah, exactly. That's a nice way to think about it. Now, what happens if it's not an equality? What happens if it's something like epsilon is bigger than 0? What if my statement is epsilon is bigger than 0? How would I negate that? So what's the opposite of greater than? What's the opposite of greater than? Yeah, Cuddler, you got it. So it's going to be less than or equal to. So the negation is going to be epsilon is less than or equal to 0. Perfect sets. Perfect sets are coming up next week, no sign. I think Slender is going to potentially talk about perfect sets, if I remember correctly. Yeah, so that's kind of the idea with these simple statements. Now, things get a little bit trickier if we have quantifiers. So it's probably best if we look at like an example, because quantifiers, usually what you're trying to do to negate a quantifier is you're swapping the kind of quantifier that you're using and you're adding in the word not to make it a negated statement. So let's take a look at a universal quantifier first. So if our statement is all squares are rectangles, so we're making a statement about squares and every single square. So this is a universal kind of quantifier. I'm making a statement about every possible square. And I'm saying that all squares have the property of being a rectangle. So yeah, if I want to negate this, I could say not all squares are rectangles, but what am I really looking for? Like if I wanted, like if someone came up to you and said all squares are rectangles, you're going to be like, bruh. Let me draw you. Oh, no, wait, this is true, isn't it? So we're good. I was thinking maybe we could argue. But if I wanted to argue with somebody, if someone came up to me and said all squares are rectangles and I disagreed with them, all I'd have to do is find a square that wasn't a rectangle. So when we go to negate this statement, we're changing the universal quantifier to the existential one. There exists a square. And then we're putting the not in the property that we're looking for. not a rectangle, right? So rectangle is the property. All squares is the kind of the quantifier and set that we're working with. So we change the quantifier, keep the set the same, and then add the word not in there to get the job done. Yeah, so Jeff's got it. There exists at least one square that is not a rectangle. Yes, perfect. Me when maths is a subject about English language. Yes, seriously, right? But I always think about it from the perspective of, like, if somebody said this statement to me, what would I have to do to disprove them? What would I have to do to argue with them? If someone came at me and said all squares are rectangles, I could disprove them by trying to find a square that's not a rectangle. I wouldn't be able to do that because the original statement is true, but hopefully that helps make it make a little bit more sense. Remind me of the law of excluded middle, Riz. Is that law of excluded middle, does that just mean that it's an either-or kind of property? Yeah, so we're going to assume the law of excluded middle here. We're not going to dive too deep into logic. But yeah, you can assume that all of the elements that we're working with are either in the set or in the set with the property or not in the set with the property. Or I guess they either have the property or they don't. The famous conspiracy theory that not all squares are rectangular. Damn. I haven't seen that on... haven't seen any tinfoil hats about that quite yet. Nice, Vin. That looks pretty sexy. Okay, so our statement now is for all epsilon bigger than 0. Okay, so a universal quantifier. We're using for all. And epsilons that are bigger than 0 are the set that we're working with. All right, so we have this set of epsilons that are bigger than 0, and we're making a statement about all of them, and we're going to say that 1 over epsilon is less than 0. So that's the property that we're looking at. 1 over epsilon is less than 0. So if I want to look at the negation of this kind of statement, take a moment to think about what you think the negation might look like. You're almost there, Cuddler. And Blob, I think you have a really good comment here. You're saying squares are a subset of rectangles, right? So we know that all squares are rectangles is true, right? So when I go to negate this statement, this new statement should be false, right? It should have the opposite truth value of what we started with. There exists a square that is not a rectangle. Well, that's definitely false. We know that all squares are rectangles, right? So this... you can kind of sometimes double check that it makes sense that way too, right? My original statement is definitely true, so the negation has to be definitely false. Yeah, so what do we got here? I need to look at my quantifier. It's a universal quantifier, so we're going to change that to an existential quantifier. So there's at least one, or there exists is a typical terminology. I'm going to keep the set the same, so I'm working with this set of epsilons that are bigger than 0. But what I want to do is I want to show that one of them doesn't have the property. So I'm going to look at the property, which is 1 over epsilon is less than 0, and we're going to swap that, to a bigger than or equal to 0. Okay, so we've negated the property, we've changed our quantifier, and we've kept the set that we're working with, the epsilons that are bigger than 0, the same. There exists an existence, yes. All right, let's do some practice with the existential quantifiers, again, just to kind of make sure you're comfortable with what that looks like. So let's say we have a statement, at least one prime number is even. At least one prime number is even. How would I negate that? Yeah, I think that's true, Cuddler, right? Lix is the integral of, it's the logarithmic integral? I think so. So close, so close. So our quantifier is existential, at least one. So I need to change that quantifier as well. So the negation is going to be every prime number, or all prime numbers. I need to change it to a universal kind of quantifier, and then add in the not. Yeah, exactly. So all prime numbers are not even. Or you could also say all prime numbers are odd because there's a dichotomy there as well. Yeah, all primes are odd numbers. Yep, 30, you got it. So either you say they're not even implies that they should be odd. Yep, that's a nice way to think about it, Cuddler. If you start with that universal statement like all, that's got to go to existential and we negate it. And usually we use like there exists as like the existential phrase. Can we evaluate the truth of there exists an infinite number of primes p such that p plus 2 is also a prime? Stop it. So last example here of negation, there exists an x as a real number, satisfying 1 over x is equal to -5. Have they proven that yet? Like, have they proved the twin prime conjecture? Haven't they proven it for, like, p plus n? I thought they've proved that already. Or am I just tripping? So in this particular case, we have existential quantifier. Let's swap that out for a universal. Let's keep our set the same. Right, so instead of there exists an x, a real number x, we're going to go for all real numbers x. And then we want to negate that equality, right? So now we want to have 1 over x is not equal to -5. Yeah, there is no real number
Brace
x.
yourselves,
That works
everyone.
too. That works too, yep. Oh my gosh, we got a little raid happening here. Jevaqua, thank you very much for the raid. Oh my goodness, welcome in, raiders. I love that kingdom key. I love the kingdom key. We're going to have a little shout out here for those of you that are chilling on Discord. Make sure I spell this correctly.
Prepare to be iterated.
Yeah! Thanks for the follow. There we go. If you have not done
Prepare
so,
to be iterated.
feel free to show some love for Jevaqua. Yeah, prepare to be iterated, exactly. How's your stream today? Welcome in. So my name's Penn Center. Welcome on in, Raiders. Today we're in our real analysis part 3 class. We're talking about some proof things right now, and we're eventually going to be talking a little bit about counting things and how there are some infinities that are bigger than other infinities. Thank you for the on-screen celebration. Oh my gosh, yes. Oh my gosh, what is going on? I wish these pop-up icons could be a part of a Cauchy sequence. Oh my gosh. Do we have the VODs of the previous lectures, Cuddler? Yes, absolutely. Yeah, so that they have bounded tails. Nice. I see what you did there, Vin. I see what you did. Yeah, so the VODs always get posted. I'll show you... Oh, damn!
Oh yeah? Prepare to be iterated.
Thank you very much for the bits, Bob. Very radical of you. So yeah, if you need help finding the VODs, just let me know. I usually post them up over the weekend. So this one should get posted up tomorrow or Monday inside the Real Analysis subchannels and the Mathematics Discord. So if you need access to those channels, like I said, just let me know. The streamer's making too much money on his own platform, and we need to monetize this. Yes, do it. The level of maths on the slides and the level in chat seem to be very different. Yeah, we try to make math kind of accessible here. We try not to get too crazy. So the last thing that might be helpful is negating a conditional statement. So if you have a conditional statement, if P then Q, to negate that, you're going to take the hypothesis and you're going to add it to the negation of Q. So we're going to take P and not Q. So I'll give you a couple examples here. If 2x is even, then 2x plus 1 is odd. So if I want to negate something like that, I'm going to take the hypothesis, which is 2x is even. I'm going to negate the conclusion and connect those things together with the word and. So 2x is even and 2x plus 1 is even. Discord just popping out about numbers being complex. Are you suggesting that the set of integers is bigger than the set of natural numbers? Ooh, that's a good question. We'll get there eventually. We will get there. There's only one way to find out. True. Find an injection or bijection. Let's take a look at this conditional statement. If there exists a delta bigger than 0 satisfying some stuff, then f is continuous. I just made this up. This may not be true. So don't judge me. So if I want to negate that, I need to take the hypothesis, which is there exists a delta bigger than 0 satisfying f of x minus L is less than delta. So we have to take that hypothesis and join it to the negation of the conclusion. Our conclusion is f is a continuous function, so we're going to join that hypothesis to and f is not a continuous function. That one's a little tricky. I object to that statement because you haven't quantified x. Fine, x can be a real number. In the second one. We can assume real numbers in the second one. We can probably assume integers in the first one, if that's helpful. Good night, Rex. Oh, I mean, good night, Turdy. What's the point of the second statement? So, in the first statement, it makes a statement about the continuity of f. Yes. I guess there's a little bit of a logic backbone here that you may not know. But if we're looking at P and Q, and P implies Q as a conditional statement, then there's a couple different potential truth values that P and Q could have. So there's a couple different combinations. So, I mean, the hypothesis could be true, the conclusion could be false, they both could be true, the hypothesis could be false, and the conclusion could be true, or the hypothesis could be false and the conclusion could be false. So there's 4 possible different cases, and we usually analyze these 4 different cases to kind of see what the implication does. And usually the only one that we really care about is this one. So this is going to be, so let me fill some stuff in here. So this one, this one, this one, and this one. So sometimes if you're taking a proof course, this is how they might define the implication, as like this kind of truth value table. So what we're looking at is we're kind of looking at this. And we're saying, like, if I want my conditional statement to be negated, right, if I want to falsify that statement, then I'm going to take P and the negation of Q, right? So I'm taking P and the negation of Q, and if I know that both of those things are satisfied, I know that my implication has to be negated. It has to be false. So that's kind of the logic backbone. I'm not sure if that helps or not. Which language should I lecture in? Damn, you're going to have to tell me the result of that one in Klingon. Oh my god. Hi, Luke. Hi, Joe. Welcome in. Yeah, we're a little bit advanced today, guys, but I do some more of the basic kind of problem-solving stuff too. So if you know you got a math class coming up, you're more than welcome to jump into stream and ask about stuff. I love talking about mathematics, and I love helping people think about their stuff. You have no math classes this semester. It's messed up. Damn. How do you survive a whole semester without maths class? Dang it. And thank you for the Chad, Zen Simplex. So we have a lovely set of mathematical streamers. All of the links to their individual Twitches are posted there into chat. So feel free to give them a little bit of love by following them as well. So by having some statement, by negating it, you get more info. I guess sometimes. I guess like the real value of being able to negate something, Cuddler, is to be able to rephrase it in a way that might be helpful for you to do proofs. And we'll see those two techniques right now. So if you have a conditional statement, sometimes it's easier to prove what we call the contrapositive conditional statement. And the contrapositive conditional statement, we create that by swapping P and Q and negating them and putting it back into an if-then structure. So the contrapositive method, we start with an original conditional statement. If I want to use the contrapositive method, what we're going to do is we're going to assume that not Q is true, and then try to show that not P is also true. So these two implications have the same truth value to them. So again, I don't have as much time to go through a lot of the logic that I would like to, but these two statements are equivalent to each other. So let's say, for example, I had the conditional statement, if 2x is even, then 2x plus 1 is odd. What I could do is I could rearrange this into the contrapositive statement, and sometimes that's easier to prove than the original statement. If 2x plus 1 is even, then 2x is odd. Yeah. So kind of swapping the order of those two statements and negating both of them at the same time. So these two should be equivalent statements. Not enough maths in computer science. What? There's I thought there was so much set theory stuff in computer science. Oh, you did your linear algebra? Yeah, linear algebra is great. And then I took I think I took discrete maths as well for computer science, if I remember correctly. That was another kind of big one. So here's another example in case you want to have a look at this. So if every rectangle is a square, then all triangles have 4 sides. Completely trolly example. But if I want to look at the contrapositive, I'm going to swap the order of those two statements and negate them. Actually, this is a good one for us to pull, to pull into OneNote. I was about to say pull out, but I thought I'd get too much. I get too much back talk for saying that out loud. So this is a really good one to kind of understand, because sometimes when we're working with quantifiers, it's easier to use specific methods. So it's nice to be able to sometimes form these contrapositive statements so that it's easy to work on some of the proofs. So what I want to do is I just kind of want to highlight a little bit about some of the stuff that's going down here. So we have kind of a statement that I'm going to underline. We have a quantifier that I'm going to put a box around. So every rectangle, that's going to be a universal quantifier, and all triangles, that's also universal too. So I have a conditional statement that has 2 universal quantifiers inside these kind of substatements. So when I want to go to create the contrapositive, I'm going to be looking at this right here, and I need to negate that and put that as my hypothesis. So how do we negate that? Well, we take our universal quantifier, turn it into an existential quantifier. Triangles that have 4 sides, that's the property. Triangle that does not have 4 sides is now our new property. Beanmaster gonna go play Metal Gear Rising Revengeance. Damn. You're so excited you put it all capital letters and you used a proper colon. Damn. Have a good night, man. Have a good night. Farm food sponsor. Fuck. You guys are hilarious. So same thing down here. Notice that we're going from this universal quantifier that we had up here. We're changing every to there exists. And then rectangle is a square, so the set of rectangles has squares being the property, so now our rectangles are not going to be a square. What does it mean for something to exist? Finally, 4-sided triangles. You've been waiting a long time for that, Joe. I know you have. Finally we can talk about 4-sided triangles. Now, is that is that just a philosophical question, Blob, or is that a legitimate question? Because I feel like if you're asking a legitimate question, I might have an answer to that. right, and the last big proof technique that I want to talk about today is called contradiction. So if I want to prove a statement truthful or false, if I want to prove that a statement is true, and it's just a simple statement like P, we can use the contradiction method, and usually all we do is assume the negation is true, and then we show that this leads to some kind of mathematical absurdity. That's kind of the technique for the contradiction method. And the logic goes something like this, right? If I assume that P is false, and this leads to a contradiction, then we're forced to conclude that the negation of P is false, which is going to imply that the original statement is true. So I only have two choices. Either the statement that's in front of me is true or false, because it's a statement. If I can show that one of those cases doesn't make any sense, the other one has to be the truthful case. That's kind of the idea. HDD, gonna go to bed, but we'll definitely try and catch more of your stream sometime. Bye. Thanks for coming in and joining the raid. Much appreciated. Good to chat with you. Oh, discrete maths are starting out on Tuesday. Damn, that'll be fun. Discrete maths is great. Okay, I'm gonna skip through this proof. This proof just kind of goes through a little bit of some of the ideas that we talked about. I'll let you take a look at that on your own time after I post the slides up. Because I want to kind of get into the cardinality stuff, because it's already been about an hour, and we're usually only slotted to go till 3. I feel like I'm going to be a little bit late today, so we'll be chilling out. we'll be mad chilling for like probably another half hour after 3. So let's talk about cardinality. If I have two sets, A and B, we say that the cardinality of A is equal to the cardinality of B, so we use these like little, like almost like absolute value bars here. And we're going to say that two sets have equal cardinality if there's a bijection. So there has to be a map that takes all of the elements in set A and sends them into elements in set B in a one-to-one kind of way. Now, if you're reading Abbott uses this like similarity notation. So he says that A is similar to B if these two sets have the same cardinality. Am I in the States? What is it? About 2 p.m. So I'm in Canada. I'm in British Columbia. So I would be the same time zone as like California or Washington. Penn says a boot. It's true. I go oot in a boot. What's a thruple? Stop it. So since cardinality typically is kind of making a comparison between like the relative sizes, we could potentially start to eke in some of the typical notation that we might have with regards to how to compare sizes of things. You have to be a little bit careful with infinities, but for finite sets, this isn't too bad. But the definition should work for these infinite sets as well, and I'm going to show you how we can use it. But the idea here is like maybe I can't find a bijection, so I don't know explicitly that A and B have the same cardinality. If I can find an injective or a one-to-one function from A into B, then I know that that B is, how do I put this? If I can find a one-to-one function mapping all of those elements into B, then at most the size of A could be B. That's kind of the idea here. At most the size of A could be B. I think that's a nice way to say it. And then of course, if you can find an injective function, but there's no surjection, so it's not onto, then there's kind of like this more strict relationship between A and B. Okay, so if I can map A into B, but I know that there's no surjection, then you can get rid of the equal sign. You know that the cardinality of A is strictly less than the cardinality of B. For finite sets, if A is a proper subset of B, then the cardinality of A is less than the cardinality of B, but yes, that fails for infinite sets. So yeah, we have to be a little bit careful with infinite sets. That's the tricky part. So usually what we're going to be trying to do is trying to build some of these injective functions, and in some cases show that a surjective function does not exist. So for finite sets, like Jeff says, these kind of follow our intuition about counting things. But what we really want to get to today is how do we count things that are not finite? So how do I deal with things like the natural numbers or the integers or the rationals or the real numbers? Like how do I deal with that kind of stuff? Hi Andy, welcome in. This is such an important topic, IMO. Yeah, it's probably one of the first like really mind-blowing things that you get to do like in your discrete maths class, for sure. So for the finite sets, like I said, things are fairly straightforward for finite sets. If A is this set 1, 2, 3, and B is this set -1, 0, and 15, well, we know that both of these things contain 3 items, so A and B are, their cardinalities are equivalent to each other. So pretty straightforward here. If I bring in a third set C that has fewer elements than either A or B, then I could write that C is less than or equal to A, like the cardinalities here are less than or equal to A, the cardinality of C is less than or equal to the cardinality of B. And then if we kind of notice that I can map all of the elements from C into B in a one-to-one kind of way, but we notice that it's not a surjective, so not every possible element of B comes from an element of C, that allows you to write that strict less than symbol here, right? So it's a one-to-one function from C into B. It's injective, but it's not surjective because this number 15 doesn't come from, something in C. By the way, why is there no arrow? Like, why couldn't I just put an arrow from 3 to 15? Why couldn't I do that? Or an arrow from, 1 to 15? Like, I can't add another arrow here, right? I can't do that. I'm glad the set of natural numbers is equal in cardinality to the set of rational numbers, or a lot of computer science would fall apart. Yeah. Yeah, if I add another arrow, I can't map 3 to 2 different things, otherwise it's not a function, by the way, right? So now, second example and third example are going to deal a little bit more with the infinite space. So let's say I take the set of even numbers, I'm going to call it fancy E, and the set of even numbers is 2, 4, 6, 8, and so on. I could actually form a really nice relationship with the set of natural numbers by just, taking all of my natural numbers and multiplying them by 2, and they land on the even number. So this is a nice bijection, right? It's one-to-one, it's onto, everything is covered. So in this particular case, because we can demonstrate this kind of nice mapping, we know that the cardinalities of the even numbers must be equivalent to the cardinality of the natural numbers. PTSD setting in. It's true, right? I know. There's so many proofs I was doing the last couple days, I'm like, I don't even remember how to do this. Graph theory wants their arrows back. No, I'm going to take them. They're mine. Okay, let's do a hard one. Let's look at the function that maps all of the real numbers from -1 to +1 into the set of real numbers. And I'm going to explicitly define a rule. So the explicit rule that I'm going to define is that f of x is equal to x over x squared minus 1. Now, it takes a little bit of work, and I had to kind of dive into Desmos a little bit here, at least for the surjective part. The injective part's not too bad. So if you remember, to prove that something is injective, we want to show that fx equals fy implies that x is equal to y. So I'm basically going to start up here by assuming that f of x is equal to f of y. I'm going to use the rule that I have for f of x, and then do a little bit of algebraic rearranging. And I can kind of factor this apart into 2 really nice factors. So I get 2 factors, xy minus 1 and y minus x. So both of these factors, one of them or both, have to be equal to 0, right? So I factored this, so one of these has got to be 0. But I know that xy can never be equal to 1. How do I know that? So this y question mark is not because I don't know, it's because sometimes it's nice to pause and think about why that's true. So why can this thing never be 0? Why is xy never equal to 1? Because if I can convince myself that's true, then y minus x is equal to 0, and I have that f is injective. It's 1-to-1. I created a mapping from natural numbers to the reals. Nice. Is it a 1-to-1 function? Jeff, you got it. Yes, both values for x and y have a magnitude less than 1. So when I multiply them together, their magnitude stays less than 1. So I can be assured that x times y will never be equal to 1. So I have a nice 1-to-1 map from this particular open interval into the set of the real numbers. Yeah, exactly. Now, for the surjective part, you have to show that every output number comes from some kind of input number. So we have to go through the construction method here. I have to show that I can find one of those numbers that gets mapped to an output number. So I'm going to choose an output number in R not 0. Now, if...
Prepare to be iterated.
Thank you very much for the follow, Joe. If R was equal to 0, I'm just going to choose X is equal to 0. So I'm going to focus on the non-zero stuff because I'm going to need to use I think I'd use the quadratic formula here to divide by, and I had to divide by R. So I want to make sure not to divide by 0 and get something super funky here. So if R is 0, just choose X equals 0, cool. And if R is not 0, but it's some other real number, then let's choose X in the following way. And then we can actually just sub that right into the rule for our function and simplify that, and we get R, right? So we can kind of show that I can construct a particular X value that does indeed get mapped to R. So the last thing we want to convince ourselves of is that this X value is inside the interval from -1 to +1. And all you really need to do here is do some basic calculus. So just maybe convince yourselves here that as R gets really big in the positive or negative direction, that should tend towards plus or minus 1. So all of these X values lie inside -1 to +1. So that proves the surjectivity. So we can always find values inside -1 to +1 that get mapped to any output value in the real numbers. So we have a bijection. So we know that the cardinalities of these two sets are equal to each other, which is kind of weird. It's kind of weird, chat. We're saying that the cardinality of R is the same as the cardinality of all of the real numbers between -1 to +1. That feels weird. You wish you were in Canada right now. Where are you, Luke? Where are you from? Yeah, so that kind of I don't know, that example always kind of freaks me out. Infinity is weird. Yeah, and the cardinality of R is equivalent to the Cartesian product of all the R's, like a finite Cartesian product. Damn, that's weird. Okay, so we do want to start comparing some of our other number sets as well, so I want to talk a little bit about countability and how we're going to be using some of these ideas and some of the proofs as we start to get into the really big portion of today's class. So we'll say that a set is finite if it's either empty or we have a bijection into a subset, a specific ordered subset of the natural numbers, right? So if I can take A and I can find a bijection to this particular subset of the natural numbers, then it's finite. Now, what could happen is I could be working with a set A that doesn't have that kind of bijection, but if I can find a bijection into n, the natural numbers, then we say it's countably infinite. So in some sense, you can kind of count all of the elements in some way inside this set A, right? Like 1, 2, 3, 4, 5. You can kind of enumerate them in a very nice way. Sometimes what we do is, like, the terminology that I typically use is, if I say countable, that usually means finite or countably infinite. So I'm a little bit loose here with the wording a bit. But what I really want you to see here is that all I really need is an injection from the set that I'm working with into n. So if I can find a one-to-one function that injects my set into the set of natural numbers, then it's countable, right? Either it's going to be finite or it's going to be countably infinite. And then if I can't do that, if I can't find such an injection, then I would call that set uncountable, right? So I can't enumerate it in a way that I want to be able to talk about it. So in some sense, I can't actually be like, this is element 1, this is element 2, this is element 3, this is element 4. So we call that uncountable. So I use this lemma quite a bit in some of the proofs that we're going to talk about. The composition of two injective functions is injective. So if I compose two one-to-one functions, the composed function that I get should stay one-to-one. Does n include 0? No, we don't want to include 0. We're not computer science savvy in these notes. All right, so if I want to show that this composition is injective, let's just go ahead and consider this map and see what happens with the composed function, g composed with f. Did I put that in the right order? A goes to B, B goes to C. Yeah, I think that's good. So we're going to start in set A. We're going to map objects into set C. And remember that if I want to show something as injective or one-to-one, what I want to do is I want to show that the function evaluated at x equals function evaluated at y implies x is equal to y. So I'm going to start with my function, g composed with f, evaluated at x and y. And I want to try to convince myself that I do indeed get x is equal to y. So I'm going to have to fill in a couple gaps here. So as I move from this first equality to the second one, that's just by the definition of composition. So how do I move from this second equality to this third equality? Like, what am I doing as I move from this first one to the second one? Maybe it's worthwhile for me to... I'm just going to copy this over into OneNote so I can make some annotations. Whoops, that's not what I want. Damn it. Damn it. Okay, so that's by the definition. So now what I'm curious about is, like, how are we moving from here to here, and how are we moving from here to here? So can someone fill that in? Riz, that's a good question. If I have an injection from x to y and another injection from y to x, are x and y of the same size? I believe so, yes. What does CSP stand for, Vin? Can you remind me? And that way Riz can look it up if they want to take a look at it. So we do have a couple things that we're allowed to assume here. We have assumed that both of these functions are injective. Right? So if f is injective, we have that f of x equals f of y should imply that x is equal to y. And that's what I'm doing here. Now the other thing I have, because g is injective, I have that g evaluated at x equals g evaluated at y should imply that x is equal to y as well. And I've actually used that fact right there. Right, so g of f of x equals g of f of y implies that those inside pieces, which are f of x and f of y, have to be equal to each other. So I'm kind of using the fact that g is 1-to-1 first, and then using the fact that f is 1-to-1 afterwards. Cantor Bernstein, okay. Injection from x to y, so the double?
Lurking in the shadows.
Thanks for the lurk, Jeff. Cantor didn't do shit, take his name out, damn. Let me think about it, Riz. So you were asking the question, so if there is an injection, so if we know that f from x into y is injective, right? So in other words, if I have this should imply x is equal to y, and you're saying there's some other function that's also injective? Is this what you're wondering? So if these two things are equal to each other, that would imply that y is equal to x. Or I guess I can use y here, that's fine. And so the question would be, do x and y have the same cardinality? Is that your question? Now, my initial thoughts on this would be something like this. I mean, if I have an injection, then I know that the cardinality of x is at most the cardinality of y, right? At most. right? And similarly, down here, if y gets injected into x, I know that the cardinality of y is at most the cardinality of x. And then, so I think that when you kind of look at and compare these cardinalities, that would imply that the cardinality of x must be equal to the cardinality of y, right? I mean, I guess they could be empty too. But the cardinality of the empty sets is 0 anyway, right? So the cardinality should be equal even in the case where we have empty sets. I think that's how we would do that. What do I think about the axiom of choice? I don't know, just choose to use it or not. He just read about a stupid hotel and made the stupidest theorem. Oh my god. All right, friends. A subset of a countable set is countable. Let's take two sets. Let's suppose that B is a subset of A and A is countable. Let's go ahead and define a map. It's going to be the identity map. So basically we're going to go from B into A, and any of the x's that are inside of B just get mapped to themselves. Okay, so it's just the identity map that just maps all of these elements of set B into to themselves. So this is just kind of a very natural injective kind of map. Now, since A is countable, we have an injective map from A to N, right, by definition. And so all we need to do now is just compose the two maps that we have. So we have the identity map being composed with map F, and that should take elements from B into the set of natural numbers. And we know that we can do that by the lemma that we just proved. So this composition is injective, so we have that the subset B has to be countable as well. Part 2 of what? Gödel's incompleteness proof? Is that what you want? Does a subset B of set A have all of the properties of A? That I couldn't tell you because I don't know what properties we're looking at. You'd have to let me know kind of what properties you're thinking of specifically. Because we might be able to break it, right? We might be able to break it. Especially if we choose B to be like empty. Sometimes taking empty sets as like counterexamples kind of breaks some stuff. All right, and then kind of the next big thing that we need here is that a disjoint union of two countable sets is also countable. So if I have these two countable sets and I take a look at their intersection, I know their intersection should be empty. And we do that just to kind of ensure that we don't have any overlaps. As long as A and B don't have any overlaps, I can kind of ensure that elements that might be shared don't get mapped to different places effectively. But since A and B are countable, we can set up these two injective maps. So there's an injective map from A into N and an injective map from B into N as well. And so all we want to do is just kind of consider what we're going to do with this map that's going to act on the union of these two sets. So I want to kind of construct a map that's going to work on the union of all of these elements, and I want to kind of convince myself that I can inject those elements into N in a really nice kind of one-to-one way. So the suggested proof that I saw said, well, why don't you just take all of the elements in A, ensure that they get mapped to even numbers, and take all of the elements in B, make sure they get mapped to odd numbers, and then, just kind of convince yourselves that H should be injective. Okay, so the question is, you said if A is countable, then the subset B must also be countable. I'm asking, is there any property of a countable set A that a subset B wouldn't have? And so no sign is saying the cardinality isn't necessarily... Yeah, the cardinality might not be equal to each other. Yeah, I can see that. But you should be able to bound the cardinality though, right? Yeah. So this connects to my previous question about uncountable sets. Is any subset of R either the same size of R or countable? Yeah, I think that's true, Riz. My gut intuition says that that's true. Because there are certainly... I mean, if we consider the empty set's countable. We know that the set of natural numbers, for example, is a subset, right, of R, so it has to be countable. Oh, but is it the same size? Yeah. Does it have the same cardinality? Yeah, I think that's true. I think you can basically take any open set. I don't know about... I suspect it's probably okay. I'd be worried about like unions of some of those open intervals getting a little bit wonky. For kind of what I talked about here, right? You want to make sure that you're not double counting when you're kind of constructing the injections, but I think that should be okay. Oh, that's the continuum hypothesis. Oh, right. Yeah, so there's no infinity between the two, right? And that's what you're referring to. Yeah. I should know that you guys sometimes are just trolling me. Yeah, Nylon told me in Twitch, an open question as to where there are infinite cardinalities strictly between M and R. Yeah, can we get a proof? Okay, that's why you're asking me if you can get a proof if it's okay. Damn you guys, you got me. You got me that time. Fine. I'll accept my defeat. All right, so let's take a look at this function h. There's three main cases we want to look at. Two cases are fairly straightforward. So if I take two elements in A, and I look at x and y, which are both in A, then I know h of x and h of y just get mapped to 2 f of x and 2 f of to f of y. Divide by 2, you know that f is injective, so you're good to go. Case 2, very similar. We're going to grab two elements inside of B, and you can kind of go through the process and show that injectivity should be okay because G is injective. The tricky case is the third case, where you take an element from A and an element from B, and you have to kind of convince yourselves that things should be okay here because elements in A kind of get mapped to even numbers and elements in B get mapped to odd numbers. So how I kind of convinced myself by working in the opposite direction. I kind of said, okay, if x and y weren't equal to each other, I know that they're not because they're in different disjoint sets. Excuse me, this should imply that h of x is not equal to h of y. So it's the contrapositive of the typical definition of injectivity. So I convinced myself that way that I was happy with that. So H should overall be injective. So now we have this injective map from the... is this correct? That's not right. This should be A union B, right? So this disjoint union A union B should be countable. So I have an error there. I'll have to fix that for you guys when I go to post the slides. All right, so with some of the stuff that we've been able to do here, we should now be able to kind of state a nice corollary. We should basically now be able to prove quite easily that Z is countable. So what we're going to do in this particular case is take the integers and we're going to divide it into two disjoint sets. We're going to look at the set of positive whole numbers and 0, as well as all of the negative numbers. So I just wrote negative n here as that set. Now, n union with 0 is just the union of two disjoint countable sets. So by our last theorem, we know it's countable. So that's taken care of. So the next thing we want to do is kind of take a look at the negative numbers. And for the negative numbers, there's a really natural bijection where we just kind of pair up things in a very, very nice way like this. All right, so we know that negative n, right, the set of all of our negative numbers should be countable. So now if we kind of dial that back, we can now basically say that Z is a disjoint union of these two countable sets, negative n and n union 0. So when I kind of put them together with theorem 2, I get that Z is countable. Hi, caller. How's it going? Welcome in. Yeah, if you want to look at that a little bit more, caller, it's called the continuum hypothesis. It is in our textbook in Abbott. They do talk about that. I think it's in chapter 2. I just can't remember exactly where. Oh, maybe it's chapter 1. Completeness. Yeah, Cantor's theorem. power sets. Or maybe it's not. If it is in the textbook, it's going to be in like section 1.5 or 1.6. Maybe I saw it when I was peeking around online for some stuff. Hi, Miles. Welcome in. Oh my gosh. It's been a hot second. How are you doing? Does K times some set A mean multiplying elements in A by K? What happened to Vin? What's going on? You need to stop bullying the person who's donating his time to the server. I don't fucking care. You guys are hilarious. Everyone loves a good troll now and then. Come on. No worries, no worries. It's all in good fun. So Andy says, I love this theorem. Super important for programmers. I'd be curious to know a little bit more about how you use some of these theorems in computer science. But yeah, I did find this one pretty important. And maybe it's the connection to the rational numbers, Andy, maybe that you're thinking about. But if A and B are countable, then the Cartesian product of those countable sets should be countable too. So let's go ahead and assume that we have two countable sets. We know we have two injections, F that'll go A into N and G that'll go B into N, right? So these two nice one-to-one functions. And then we're going to kind of construct what I would consider a very natural injective function. And I'm going to call it H. And it's going to go from the Cartesian product into N squared, or N cross N, right? Or N Cartesian product N. Okay, and I'm just going to define H like this. So what we really have to do now is, if I could show that N Cartesian product N is countable, then I kind of have the relationship that I need. I know that the cardinality of the Cartesian product of A and B could be no more than the cardinality of N. So that's kind of what we're going to try to do. We're going to try to construct some kind of one-to-one function from N cross N into N. And there's some really cute ways to do this. I particularly like this one. I thought it was really cool. Basically, we're going to take an ordered pair in N cross N, and we're going to map that to 5 to the M, 7 to the N. And if we do that, we can kind of check to see if L, the map L, is injective. So let's set up L of M1, N1 equal to L of M2, N2, see where it goes. And then we can just convince ourselves that since 5 and 7 are prime numbers, then we should have unique prime factorization. Okay, so we have that our two tuples must be equivalent to each other, so L is injective. So I thought that was kind of a cute little way to explain that really nicely. Since L is injective, now you have a composition of injective functions, so A cross B should be countable. So that'll finish up the proof that the Cartesian product is countable. If I were to cut If I were to cut 40% of my liver off and eat it seared and spread on brioche with orange marmalade, would it taste good? Probably. I mean, people eat liver all the time. Doing it right now. Please let us know how it goes. Please let us know. So Andy says, suppose you want to search for something using a computer. You can imagine any search as f of x equals 0 and kind of cycling through the x's. Some problems are easier to formulate with x as a pair or a tuple. Oh, okay. Joe Pop, what? Give it the fucking like drooling face for the... Is it human foie gras? That's the question we have to answer. Is it human foie gras? I think so. I think that might be how you describe it, yeah. And so with the countability of the Cartesian product, you can kind of make this really nice, straightforward corollary. Oh, why is that there? I need to get rid of Discord. Oh, we don't need that there. You can make a really nice corollary and just kind of argue that Q is countable. So the easiest way is just to kind of understand that there's this really nice injective map where we can map any fraction into a two-tuple, where the first component here is inside of Z. It can be basically any positive or negative number and 0. And the second component is Z not 0. So we don't want n to ever be 0. The only other thing you have to restrict yourself to here is that you do need the GCD of these two numbers to be equal to 1. And that way you don't get any kind of funky, like, ill-defined or like, how is that going to break? So like the GCD has to be 1 because you don't want like f of 1/2 to map to somewhere and f of 2/4 to map somewhere else, right? When they're really the same thing. So you just want it to be kind of well-defined, right? In a nice one-to-one way. So we're adding in that extra restriction of the GCD being 1 so it doesn't kind of fuck us over a little bit. And then now we just have an injection from Q into this Cartesian product. We know that Z's countable, Z less 0 should be countable. So now we know that Q is countable because it can be expressed as a Cartesian product of countable sets. A liver can regrow to a normal size even after up to 90% of it has been removed. Wow, infinite food hack. Infinite food hack, damn. Cuddler, yes. M and N should be coprime, yes. I can't believe... why haven't we just been eating our livers this whole time? Like every day we could just shave off some percentage of our liver and just go for it, yeah. 40% for me and 40% for my fiance. Damn, you can feed the whole family with one liver, chat. This is crazy. This is wild. Okay, so here's the big daddy, what we really wanted to get to today. Well, I'll probably take a little bit of a break after this just to hit the washroom, and then we'll come back and we'll talk a little bit about the sequency stuff, which is, I want to get that out here for Slender as well. I'm gone for a few months and he turns into a cannibal, true. You guys are killing me today, you're killing me. So this is Cantor's theorem. Cantor's theorem says if A is a set, then the cardinality of set A is always strictly less than the cardinality of the power set of A. This is kind of a big deal. For finite sets, it's not too bad, right? If I have A as the empty set, then the power set of the empty set contains only the empty set, and then the relationship is true, right? The cardinality of the empty set is defined to be 0 typically, and since there's one element in the power set, we have the cardinality of the power set's 1, so you have this relationship here that ends up being super nice. And in general, for finite sets, it's not too hard to convince yourself that this is true. So if you've taken a course in discrete maths, you know that the cardinality of the power set of A is 2 to the n, and that's true when A is finite, right? So kind of maybe try to convince yourselves why that is true. It's kind of a fun little counting problem. And so you definitely have that this is satisfied for finite sets. So what we really want to think about before we take a little break is like, how does this work for infinite sets? Or like, how is this going to work for infinite sets? So we're going to try to set up a contradiction. So let's assume that we can get a bijection from the set A into its power set. Ooh, sum of binomial coefficients. That's fun. Is that true? Can you do that? 1 plus 1 to the n? That's crazy to me. Using the binomial theorem to do it? I guess so. I guess because you have like two choices, right? It's the same thing. Okay, so let's assume we have a bijection. We're going to construct a weird set. So S is a set, and it's going to contain all of the A's inside of set A, such that A is not an element of G of A. Now, this part over here was really confusing to me, and it took me a long time to figure out what the fuck they were talking about. So let's like kind of look at this statement a little bit and kind of decompose it a bit and see what they're talking about. So remember that this G function goes from A into the power set of A. And A is probably infinite in some kind of way. But what we're really looking for is we're really looking for all of the A's inside of set A, where A isn't inside of G. So G is going to be acting on elements of A, and the outputs are actually going to be sets, right? So this is like a set of elements. Like, I saw this and I literally thought I was tripping. I was like, what in the world are they talking about? And then I realized that the power set is a set of sets. So the inputs are always going to be an element, and the outputs are always going to be a set. So we're specifically looking for the G of A's, where like A does not land in here. So like any of these elements, like it does not contain A. That's what we want. Okay, so hopefully that makes sense. It took me a long time to figure out what the heck that was talking about. I was like, did they write this down wrong? Like, what the hell? I need a second to note this proof down on my abacus. Damn. Do I still have an... I gave out abacuses one time. I don't know if I still have one here. All right, so let's kind of take a look at some of the properties of this set that we've constructed. So S is contained in A, right? S is a subset of A. How do we know that? Well, because S has only elements from A in it. So either it's all of A, or it's a subset of A. Right? So that's true. If S is either all of A or a subset of A, it's got to be in the power set of A. That's all I'm saying here. And so we have assumed that there's a bijection from A into the power set. So that means that G is both injective and surjective. Since C is surjective, it must be that there's an X inside of A that lands on this particular set, right? There's got to be some element in A that gets mapped to this particular subset of A because we've assumed that G is a bijection. An abacus is one thing. One day I'll drop the money on a curda. What's that? And then I'll be unstoppable. Well, now I'm curious. Were you worried that your students had lost track of real maths while doing fake maths like algebra? How dare. How dare. Can someone explain to me what's a curda? What is that? What are you talking about, Nylon? So let's take a look at the cases. So either X is inside this set or it's not, right? X is an element of A, and we've kind of posed this particular weird-looking set in such a way that, you know, we're going to kind of maybe scan through all the elements of A and see if it's inside of set S or not, right? So it's got to be either in set S or not in set S. Now, if X is inside of this particular set, well, we know that X is not an element of G of X because it's a part of S. But we know that G of X gets mapped to S because of the surjectiveness of the function G. So it's got to be that X is not an S. So you run into this weird contradiction. And so I put this illustrative example down at the bottom to kind of explain. And like I said, it took me a long time to figure out what they were talking about here. And I had to like write out some examples to be like, what in the hell are they doing? So check it. If X is in S, what does that mean? So our illustrative example has a set A. We're just going to do a finite example in this case. So I've just done 1, 2 so that I can find the power set really easily. So the power set is either empty, 1, 2, or both 1 and 2. And let's suppose that I just make a mapping from A into P of A, right? So A contains these two elements, 1 and 2, and I want to assign them to something in the power set. So I'm just going to make a blind assignment. I'm going to say just assign G of 1 to the set 2 and assign G of 2 to set 1, comma 2. And I claim that if this is the case, then S is the singleton set 1. So what would be the stuff that's inside of set S? Well, it's either going to be 1 or 2 or nothing. And what I'm doing is I'm looking to see what's going on here, right? So is it true that 1 I want to kind of make a comparison. I look at G of 1, and I know that G of 1 gets sent to this set 2. So is it true that 1 is not an element of G of 1? Yes. So we add 1 into set S. Boom. And then we do the same thing with 2. So we look at G of 2, that gets sent to 1, comma 2. And is it true that 2 is not in G of 2? Well, no, it's right here. I see it. So that's it. That's where set S comes from. So 1 is the only element that's inside of S. So what we're saying is if a number ends up being inside of S, it's actually not in S. It can't be in S. It's a contradiction. So how does that contradiction work? Right, so we've formed S. We're taking a look at 1. But it can't be that G of 1 gets mapped to this subset, right? G of 1 is not mapped to S. G of 1 is not S. It's just the way that, it's just how this set S works, right? G of 1 can never be this set S. So that's kind of like hopefully that helps kind of clarify what's happening here. And then you go through something very similar with case number 2. Right? You say that X is not an S. Right? So in this case, we formed our illustrative example. 2 is not an S. And we note that G of 2 is not S either. So you kind of construct this weird set, and you've basically shown that it's impossible for any of the elements inside of set A to actually get mapped to this set S. Like we can never map an element to set S. So we've basically shown that G can never be surjective, right? At best, it can be injective, but it can never be surjective. It's never onto. So we have this relationship now, since we don't have a surjection. I know that the cardinality of A cannot be bigger than or equal to the cardinality of the power set. So the last thing that we need to do is just show that there is a one-to-one function that goes from A into the power set. And the easiest way to do that is just to assign every element to its subset inside of the power set, and that'll finish off the proof. So now we know that because we can't find a surjection, that's why we have this kind of strict inequality between the cardinality of set A and the cardinality of the power set. Yeah, kind of crazy, right? Hey, Lucas, welcome on in. How are you doing? And so the last thing that I am going to do here before we take a little break is I just want to show you that R is not countable, and we can actually I'm going to show you a bit of an interesting way that I kind of pondered about over the last couple days. And it has something to do with mapping things and using a binary representation of things. And there's some really kind of interesting things that pop out of doing that. So I defined this thing called an indicator function of the subset that we're working with. And basically, it's just a function that maps n into the set 0, 1. And I basically want it to be on, right? I want the indicator to be on if X is inside of the subset S, and I want it to be off if X is not inside the subset S. And so the idea here is we're using the indicator function to create a sequence of numbers, a sequence of zeros and ones. And we're just kind of going through all of the elements of n, right, the natural numbers, and we're either saying like, yes, it's in the subset 1, no, it's not in the subset S, 0. And we're just kind of going through every possible positive integer number in doing that. Right, so for example, if my set S is 2, 3, 4, 5, and so on, then the indicator function evaluated at 1 would be 0 because 1 is not inside this subset of n, but it would be 1 otherwise, and we get a sequence that looks like this, 0, 1, 1, and so on. That'd be our sequence that the indicator function would give us. And we can do something similar. Let's say our subset of n was just strictly the number 1. Then the indicator function for this subset would say, yes, 1 is inside the set. No, 2 is not inside the set. 3 is not inside the set, and so on. And we'd get the sequence 1, 0, 0, 0, and so on. That would be our sequence with that particular subset and the indicator function. Now there's one kind of last thing that I want to talk about here before we get into the proof, and I want you to kind of understand the main problem that arises when we're trying to construct the injective function that we're going to be trying to construct. So what we want to do is we want to take these sequences, and we want to think about them in terms of binary decimal representations. So something like 0.011 and so on, we could think about this as each one of these like decimal places as a negative power of 2. So I get 0 times 2 to the minus 1 plus 1 times 2 to the minus 2 and so on. So we're using kind of like a typical representation that we might in computer science. And let's think about this number in base 10 so it's a little bit easier for us to kind of understand what this number is. So this would be 1 over 4 plus 1 over 8 plus 1 over 16 and so on. Now, does this converge to something? If I add up all of these fractions, does this converge to something? So that's I'm going to pose that question to you for a hot second. Now over here, for this particular sequence, I just get 0.1. This one's straightforward. This is just 1 times 2 to the minus 1. This is just a half. Would you want a Twitch trailer? I'm creating something with everyone's clips and putting it together into a trailer just for practice. Yeah, if you want to do that, that'd be cool. I would love that. What's the definition of a half? You stop that. Maybe we will do Boolean Fourier analysis. Damn, that would be fun. Just over a field of characteristic 2. I want to see it too, Andy. I think that'd be pretty cool. Now over here, it might not be super obvious, but this is a geometric sequence. So all of this should converge to 1 over 4, 1 minus 1 half. Or I'm using a over 1 minus r. And I know I can do that from calculus because this r value is, the modulus of this r is less than 1. Make a compilation of all the shit posting, no sign says. Yes, please. Just a complete brain rot trailer. All right, so we get 1/4 divided by 1/2. And as we all know, we can just divide the numerators, divide the denominators, and get 1/2. So something interesting happens when we're using this binary representation of things. And that is that two sequences, so in our case we had 2 different sequences in binary, could come out to be the same thing, right? So these are kind of 2 different ways to represent the same number in base 10, right? So there are 2 different ways. To represent the same number. And this does happen a lot when we're working with decimal representations, right? Like 0.9 repeating is equal to 1. You kind of lose a little bit of that uniqueness, I guess, of representation of numbers when you use this kind of representation. It is something that does happen in decimal as well. So this is not unique to binary, but it is something that we have to be aware of. And I'm not going to prove this, But if you get an infinite tail of 1s, it turns out that you can always look at that geometric sequence that you get, and you can always change that into a different kind of representation where we have a terminating decimal in binary. So when we go to do this proof, we're going to treat the tail of 1s as a separate case when we go to work on this proof, because there's something interesting about this tail of an infinite number of 1s that leads us to a potential not one-to-one function. So that's the problem that kind of pops up when we go to take a look at this proof. All right, so let's show that R is not countable and take a break. Yeah, you got it, Jeff, right? So if you have an infinite tail of 1s, you can always kind of round, right? Kind of move all that infinite tail, and you always get like the 1 in the 0 column right before it, right? So, how do we prove that R is not countable? Well, let's start with Cantor's theorem. Cantor's theorem says if I want to compare the cardinality of n to the cardinality of its power set, what we have is this strict relationship. So the cardinality of n is strictly less than the cardinality of its power set. So this means that the power set of n is not countable, right? Because its cardinality is strictly larger than that of the natural numbers. Now, what we could do is we could maybe use this to our advantage. So if I could somehow find an injective function from the power set of the natural numbers into the real numbers, then we'd be in business, because then I'd have this kind of relationship, and that would imply that the cardinality of n would be strictly less than the cardinality of the reals, right? That would imply that R is uncountable as well. So our real goal for Theorem 4 is just to show that the power set of the natural numbers can be injected into the real numbers. Okay, so what we're going to do is we're going to use that indicator function. So for any subset of S, we're going to use our indicator function, f sub S, and we're going to define that sequence that we talked about by kind of looking to check and see if that n value is inside of the subset, right? 1 if it is, 0 if it's not. So we're going to get two possible cases. Case number 1. It could be that this sequence that we get terminates with an infinite sequence of 1s, right? I could get an infinite sequence of 1s somewhere inside of this particular sequence. And so what we're going to do is we're going to map that in the following way. We're going to take that sequence that we get and map it to the number 1, S1, S2, up to Sk, where k is the last non-1, right? So Sk is 0 in the case that it's just a complete infinite sequence of 1s, then it's just 1. And, we don't have any follow-up SKs. But the idea here is you're going to kind of scan through. If it eventually terminates in a bunch of 1s, there should be a 0 somewhere there beforehand. And we're just going to map this in a particular kind of way. And so we're going to say that this particular binary number, right, it's going to be a binary number in terms of 1s and 0s, is always going to be greater than or equal to 1 in base 10. So that's case 1. How do we work with the stuff that has an infinite sequence of 1s at the end? We convert that into something that's bigger than or equal to 1 in the real numbers. For case 2, we take this sequence and we can actually convert it into a decimal number, a binary decimal number. Okay, now in case number 2, we've kind of assumed that we don't have this infinite tail of 1s. So I can always kind of scan, I can always just kind of map this in a really, really nice way into this binary decimal number, and it ends up being unique. And these things are always going to live somewhere inside 0 to 1. All right, so again, kind of that edge case would be if all of these were 0s, right? So if I had like the empty set as S or something like that, then, at worst I might get 0, but I'm never quite going to land on 1, right? All of these should be... Can I land on 1? No, I can't land on 1 because the only way that I could land on 1 is if all of these were 1s, right? But we've taken care of that case over here. So there is no overlap between the two cases. This decimal number, according to base 10, is always going to land between 0 and 1, including 0 but not including 1. So basically, we're just going to kind of appeal to Theorem 1, which says the composition of your injective functions should be injective, and basically you've mapped all of the subsets of the natural numbers into R in a very kind of interesting way, and now you have the relationship that you want, so R is uncountable. Damn! Yeah, like I said, Jeff, it took me a while to kind of piece my way through this, but yeah, there are a couple of the weird fringe cases that we have to kind of be careful about. But yeah, once you're careful with those kind of weird fringe cases, you should be okay. Let's see, we've actually been going for a couple hours, my friends, so it's getting late here. Tell me if you got to ultra filters. Oh my gosh. So for those of you that are on the Discord chat, we're going to pop over to Twitch and finish things up over on Twitch. Kowalski analysis. So I'm going to be closing up the real analysis meeting number 3 over on Discord. Thank you very much to everyone on Discord who came in and said hello. If you want, you can pop over to Twitch, and we'll be finishing that up over there after I take a little bit of a break. So we're going to do a little bit of an ad roll here, so you know what's going on, guys, if you need to. Let's see. Oh, that's disconnect quietly. No, just disconnect and end. That's what I'm looking for. Ba-boom. There we go. We should be good to go off of Discord. So I'm going to run a little bit of an ad roll here, so if you guys want, you can grab a QED point, and I will be back after a short little washroom break. Everybody go pee, everybody get hydrated, everybody grab a snack, and I'll be back.
Time for a pop quiz. Hardly even a practice test.
Hi everybody, welcome back. We're about 1 minute out from our little break here. Are we still going on about the continuum hypothesis? Damn. Be honest, who snacked on liver during the break? Oh my god. Bruh.
Bruh.
Hope it grows back. Aw, showing your appreciation for Showbot? Appreciate you too, fam. Showbot is still off because Technically, we do have to put this up on YouTube. Although I'm probably going to get, like, complete copyrighted because I forgot to turn off my music. Whoopsies. Oh, well. We'll put it up anyway. All right, we back. Welcome back, everybody. So I did promise Slender and Coffee that I would kind of keep on trucking through some stuff today. I want to talk a little bit more about some sequence stuff that might be helpful for real analysis. And some of the topological arguments that Slender's going to be chatting about next week. So let's do a quick little review of some of the sequence stuff that Dingus showed us last week. So we had the axiom of completeness, which is that every non-empty set of real numbers that's bounded above has a least upper bound. And then from there we kind of built out a bunch of stuff, right? We kind of constructed the set of real, or at least constructed like square roots, for example. So the axiom of completeness allows you to make some really nice constructions over the real numbers. We have the NIP. We talked a little bit about the NIP, which is the nested interval property. And so it's this idea that if you nest intervals that are closed, right? So we have to include the endpoints, and you keep on nesting subintervals like so, and you kind of keep on doing this, then the intersection of all of those closed nested intervals always contains at least one element, so it's non-empty. Need some more coffee yourself? Yeah, I feel you on that one. I was like, it's 3 o'clock, I can have a beer, right? Like, a beer is okay. It was either a coffee or a beer. I opted for a beer. We had the idea of a sequential limit. So we looked at limits of sequences. So we'd say a sequence of real numbers indexed over our natural numbers converges to some kind of real number if for all epsilon, all positive epsilon, there exists an n satisfying the following implication. So whenever n is bigger than or equal to capital N, that has to imply that we can basically get as close as we want this distance, right? So the distance from a term to A has to be as small as we want. So over here on the left, we have kind of a little diagram of what that looks like. So eventually, we have to be able to find a capital N where all of the terms afterwards fall inside of this epsilon band is usually what I call it, but Slender is going to be calling it like an epsilon ball. So that's kind of the idea, right? So eventually I should be able to do that if this sequence converges. Now we also took a look at bounded sequences and some of the properties of bounded sequences, and we say that a sequence is bounded if there's a real number where the absolute values of the terms are always less than m, right? For any, for basically all of our index numbers here. Now, if a sequence converges, it's naturally bounded. We proved that last week. But the idea is if a sequence is bounded, there's some kind of upper threshold, right? And I know that all of my terms have to be kind of bounded, right? Like bounded by that particular threshold. That's the idea. Now, sequences can be a little bit funky. They can bounce up and down and move around. I didn't mean to rhyme. That was weird. They can bounce up and down across the x-axis a little bit. And that's why we kind of consider the absolute values here, right? So we're usually kind of projecting these terms up into the positive realm and saying there's kind of some upper bound where all of our terms would naturally have to stay underneath. The intersection of closed intervals sounds vaguely topological. Yeah. Hopefully, I wonder if Slender will prove the topological version of the nested interval property. That would be fun. All right, so I want to talk first about the Monotone Convergence Theorem and what that gives to us. So if I have a sequence, if the next term in the sequence is always bigger than or equal to the previous term, that for all of our natural numbers, then we call this an increasing sequence. If the next term is always smaller than or equal to the previous term, then the sequence is decreasing. And then as long as it's doing one or the other, we usually call it monotone. So it's got to be either always increasing or always decreasing, and then we kind of slap this kind of catch-all term, which is monotone, because a lot of these proofs are done very similarly with very similar arguments, just kind of negating everything. So this is I pulled this picture back here again. This is an example of a monotonically increasing sequence. So it's monotone and it's increasing as n gets bigger and bigger. So one might suspect that if I have a increasing sequence, right, so it's monotone and increasing, and if it's bounded above, you might suspect that it has a limit. And that is true. That's what we call the Monotone Convergence Theorem. So if your sequence is monotone and bounded, then it's going to converge. And I don't remember this proof being super taxing. So let's just assume that our sequence is increasing and bounded. You can kind of walk away today if you want and do the decreasing case. It's really similar. So I'll leave that as an exercise to the viewer. And what we're going to do is we're going to take a look at this sequence. We're going to basically say that since we could kind of stuff all of these real numbers into a set, and we know that it's bounded, the axiom of completeness says it has a least upper bound. So what we're trying to do in these first couple of sentences is get a candidate for the limit, what we think the limit should be. Now, if we're always increasing, and we have kind of an upper threshold, it makes sense to take that upper bound potentially as the limit, but it could be the case that we're increasing in monotone, but the upper bound that I have is like way up here. So that's kind of the fringe case, is, you know, my capital M could be too high. So what I actually want to do is I want to look at the least upper bound. So in the case that M is not the limit, we're going to look at the least upper bound. That's going to be what we want to talk about with regards to this proof. Now, if S is our least upper bound, I know that if I subtract a small positive value from S, then I'm going to land inside of set A. So I'm going to just kind of index and say, like, there's going to be some capital N where this inequality is going to hold. Otherwise, S minus E would be the upper bound. We could just define a new we could define a new soup, a new least upper bound, if this inequality if it wasn't there. So with that inequality, and with the fact that we know that our sequence is increasing, we can kind of put together this string of inequalities. So we grab our first inequality, we know that our sequence is increasing, we know that S is the least upper bound, so it has to be bigger than or equal to all of our A sub small n's. And then, of course, since epsilon is a positive value, we have a kind of strict inequality between S and S plus epsilon. And so now you've basically kind of constructed this epsilon band, and you can now kind of pull it back together, and you can say that the difference between AN and S is always going to be bounded by epsilon. Right? So AN minus S is always bounded between negative epsilon and positive epsilon, is kind of how that works. So that's the definition of a convergent sequence, so we are good to go. You had a friend who always called it a lub instead of a soup. It drove me crazy. Yeah, least upper bound. I think when I took this course, it was lub. Yep, lub and greatest lower bound, GLB. Yep, lub and glubs. Replace closed intervals with non-empty compact. That's the word, compact and closed, right? Yeah, so hopefully we get to talk about some of that stuff next week. I'm super excited about the top topology stuff, because it's been a long time since I've done topology, so it'll be fun to revisit some of those ideas a little bit in more detail. So that's the monotone convergence theorem. It basically says if I have a bounded and monotonic sequence, it should have a limit. Awesome. So that one's very intuitive. This one's not as intuitive, the Bolzano-Weierstrass theorem. Before we talk about that theorem, let's talk a little bit about what a subsequence is. So if I have a sequence and I index, instead of using index 1, 2, 3, and 4, I'm going to use the index n1, n2, n3, and so on. And n1, n2, n3 are going to be natural numbers, but they might not be 1, 2, 3, and 4. Like, for example, n1 could be like 2, n2 could be 5, n3 could be 7, and so on. I just need these indices over here to be an increasing sequence of natural numbers. And then once I have that, then I can kind of create what we call a subsequence of the original one. And so this little I here is there just to represent that we're indexing by the n i's instead of by n. And just as a little remark here, if I have a subsequence of a convergent sequence, that subsequence should converge to the same limit. Normally that would be something that we would prove, but we've already gone a little bit over our time today, just to kind of make sure that everyone's taken care of for the next couple weeks. So if you want to read that proof, they do have it inside of Abbott, and it's definitely worthwhile to take a look at that one. So, what does a subsequence mean intuitively, and how do I think about it? Well, if I have a sequence, I'm going to call this A1, A2, A3, and A4, and so on. Oops, that's A3 twice. And so what we want to do is we now want to kind of choose N1, N2, N3, and so on. I'm just going to do maybe a couple examples so you can kind of see what this looks like. So maybe I pick N1 is actually 3. And then maybe I pick, 5, and then I pick 10. All right, so here's my sequence of natural numbers that's kind of ordered in a nice way. And so now my sequence, A-N-K, or A-N-I, is how I wrote it down in the example, would look like this. It would be A3, A5, A10, and so on. So I go to A3, A3 is a third, then I go to A5, A5 is a fifth, then I go to A10. Based on the pattern that we have, A10 would be a tenth, and so on and so on. So that's how we kind of make a subsequence. It's pretty intuitive. If you happen to know like the closed form formula, for example, we can usually write down exactly what that subsequence would look like. Now we could get crazy, like I could pick, 10, 100, 1,000, if I wanted to, and so on. In which case our A-N-I would be A10, A100, A1000, and so on. So 1 over 10, 1 over 100, 1 over 1,000, and so on. So there's a couple examples, but the idea is you're looking at the sequence that you have, picking out samples from it, and arranging them in the same order as the original sequence. So it's a bit of a complicated definition, but that's effectively what we're doing. Now, the surprising thing about doing that, or at least the surprising thing about thinking about kind of subsequences, is we get this really interesting result. And it says that provided my original sequence is bounded, there's going to be a convergent subsequence in there. And it's not super obvious why that's the case. It's not super obvious. So I want to give you a sketch of how the proof goes. And remind me at the end of this, we'll take a look at the Bolzano-Weierstrass wrap. The proof of the Bolzano-Weierstrass theorem is really cool. It is really cool. So the sketch is something like this. We're going to assume that we have this bounded sequence. So what does that mean? That means that there's a capital M as a real number that's going to bound all of my terms, right? So all of my terms are going to fall between negative M and positive M. And then what we try to do is we try to break that interval from negative M to positive M into subintervals. And we're going to include the endpoints of those subintervals, and we kind of keep creating these nested subintervals in a very, very particular way, let's say. Okay, so they're using little s and capital S to talk about the endpoints. But if this sequence is bounded, in our case, we know it's always going to be between negative M and positive M. And the dots here are representing, on this real number line, kind of where our sequence is going. So notice that there's like some that are kind of like out here far, out here far. And because this is a sequence, I don't really know exactly where this might land, but you're noticing like this big collection of potential dots in here, right? And that's going to be important. So what we do first is we take that interval and we break it in half. Okay, so break it in half. And what we're going to do is we're going to look to find the half of that interval that contains the infinite tail of our sequence, right? So since if I look at the right-hand side, there's 1, 2, 3, 4, 5, 6, 7. There's only 7 dots over here. It looks like this half over here contains the infinite tail. So we're going to make that half I2. Okay, so now we have a smaller subinterval to look at. We're going to break that smaller subinterval in half, and we're going to check to see which half contains the infinite tail. Since the left side has only 1, 2, 3 dots, we know that the right-hand side contains the infinite tail. Right, so now that's our I3. And we keep doing this. We keep taking our subintervals, breaking them in half, and checking to see which side contains the infinite tail. And we keep doing this ad infinitum, and the idea is that at each place along the way, there's always going to be some number in the subinterval, right? So we can kind of choose our subsequence in a particular way. So I can choose a number inside this infinite tail, right, of the first interval. And then I can choose a number in the infinite tail of the second interval. And then, once this one's broken in half, I can choose a number from the infinite tail. So we're constructing this subsequence by always looking at the half that has the infinite tail and just choosing a number there. And we can do that with the axiom of choice. So if we keep doing this over and over again, the nested interval property is going to say that the intersection of all of these is non-empty. Cool. So there's got to be something in that infinite intersection. One of those elements inside that infinite intersection has to be the limit of the subsequence that we've created. So that's kind of the idea. That's how we kind of finish off the proof, is you basically take an epsilon. We know that the lengths of the subintervals tends towards 0 because we're halving it every single time. And then you just have to choose capital N so that your k is big enough so that your subinterval lands inside the epsilon bound that you're looking for. And then there you go. You've constructed a subsequence. You've kind of figured out that the infinite intersection has to be, like an element from the infinite intersection has to be the limit. And there you go. You've kind of finished off a sketch of the proof of the Bolzano-Weierstrass theorem. Very, very pretty. Very, very cool. Very, very cool theorem. And from what I remember, we tend to use it quite a bit as well, right? This idea that as long as you can bound an infinite kind of thing, there's got to be a subsequence in there that has a limit. That's pretty cool. Convergent subsequence in there. I love that. I think that's great. You don't need choice, do you? Maybe we don't need choice. I was just thinking, like, there are, when we take that half of that subinterval, there's an infinite number of things in there, so we have to be able to pick one of those things, right? I'm trying to remember what does choice give us? Let's just look it up and clarify. Because I think this is a good question. I thought that maybe we needed choice. So axiom of choice. With each set I represented as a jar and its elements represented as marbles, each xi is represented as a marble. Colors are used as a function association. Oh, is it a function association kind of thing? What's the actual? Informally put, the axiom of choice says that given any collection of sets, each set containing at least one element, right? So that's what we have. It's possible to construct a new set, right? In our case, we have these infinite tails, right? And in each of these infinite tails, I have to be able to create a new set by choosing elements out of those subintervals, right? So I think we need the axiom of choice here, right? It's possible to construct a new set by choosing one element from each set, even if the collection is infinite, right? That's the tricky part. So I do think we might need the axiom of choice here. I think we might need it. Right? Like, because the question is, like, how do I know that I can choose these elements in a particular way, right? I have to be able to choose them and index them in a nice way. So I think we might need axiom of choice there. I've lost my marbles more times than I can remember. Hi, Anders. Welcome in. How are you doing? We're just finishing up our third presentation, man. Since the naturals are well ordered, you shouldn't need... Oh, I think you can just take the least natural n that falls in the relevant interval. Oh, that could be true. Yeah. That could be true. So Jeff is saying it's infinite but countable. Yeah, okay. So because they're countable, we're a little less worried about choice. Okay, gotcha. Okay, so we're not as worried about the choice part of it because they're countably infinite. If I'm interpreting what you're saying correctly, we care less about the axiom of choice because it's countably infinite. Thank you for the follow, WS Ponders. Welcome on in. Hi, Dias. How are you doing? I haven't seen you in forever. There exists blank such that blank give me PTSD to the epsilon delta definition of a limit. Damn. Then you're in for a wild ride because we're going to talk about Cauchy sequences to end off class. Ah, thank you, Jeff. So, yes. The well-ordering property. Every subset of natural numbers has a least element. Right. So the well-ordering property will give us what we need for Bolzano-Weierstrass. Thank you. If you have a rule to pick the elements of the sets, then you don't need choice. Yeah, so in our case, so Anders, and again, I'm interpreting what I'm reading in the chat. Because we have the well-ordering property, we can always take the least element. So we don't need choice in that case. And feel free to correct me if I said that incorrectly. Long time no see. You're doing good. That's good to hear. Haven't been able to catch your streams while at work anymore. No, just stream at work. Just throw it up on the big screen at work. How am I doing? I've had a tough day. I'm not gonna lie. I was prepping to get this presentation ready for everyone. It's been a long week too, right? Thursday and Friday I felt like a tornado just ripped through my office. But I mean, otherwise I'm doing really good. I love doing this stuff for you guys. It's nice to be able to kind of stream on a Saturday afternoon and have 20 people in the chat. I think that's crazy. People do stream at work. It's true. I see people co-working all the time. If I ever become a data scientist, I'm gonna just stream whatever I can so you guys can see how I'm doing data science stuff. And by the way, hi Gold, welcome in. I can't wait to talk to you later. How was the gym? I hope so too. I think February is going to be a much more chill for me. January was a really, really hard month because the first 2 weeks was all student seating for registration, and then I had a week where I had to do crazy curriculum development and pass a bunch of stuff, and I feel like these last 2 weeks I've been trying to just kind of catch up from those first 2 weeks. Well, and then of course the whole real analysis thing too, right? Organizing the real analysis group on the mathematics server, which was both a blessing and a curse at the same time. I love those guys. They've been so generous with their time and ability to help. So mad shout outs to the Mandelbrot mathematics server. If you're here from Mandelbrot, welcome in, and thank you for your support. Your birthday's in 2 weeks? Shit. Are you a Valentine's Day baby? Okay, let's finish this off so we can just chill and talk about stuff. A sequence is a Cauchy sequence if for every epsilon bigger than 0 there exists some capital N, such that m and n, when they are bigger than capital N, that's going to imply that am minus an is less than epsilon. What the frick does that mean? Am minus an. So notice, I'm going to remark that the definition of a Cauchy sequence does not rely on a limit. The usual definition of sequential limits relies on that limit existing, right? And being able to kind of bound terms in a specific way. It's the regular definition of a limit is almost saying the difference between the limit and the sequential terms is always less than epsilon. That's what it's saying. Now the Cauchy sequence is different because it's saying the difference between after a particular capital N, all of these terms, the difference between all of these terms is less than epsilon, which is kind of wild. So it's the definition of a Cauchy sequence to me, it's more about the interaction, the eventual interaction of the differences between the terms in the tail, if that makes sense. So it's less about how the terms interact with the limit and more about how the terms interact with themselves after a certain particular point. Cauchy, yeah, or as we say in the mathematics community, Cauchy. Cauchy. Are you feeling very Cauchy today? And I think, like, if you kind of dial back, it's helpful to have a definition like this, because this definition doesn't rely on the limit at all. All we're doing is we're saying, well, as long as the difference of the terms eventually is bounded by epsilon, we're good. All right, that's kind of what Cauchy is saying. Goated definition. Yeah, it's been a long time since I've worked with Cauchy sequences, but let's prove that this sequence, 1 over n, is Cauchy. So what we want to do is we want to, I think I ordered it wrong, but the order shouldn't matter because I can factor in -1. But basically I want to look at the difference of the kind of tail terms, right? So I'm going to take a 1 over n and a minus a 1 over m. That's the kind of difference of these kind of tail terms. And I know that I can kind of break this apart by the triangle inequality. So what I want is I want the difference to be less than epsilon. So what I'm kind of after is each of these absolute values, 1 over n and 1 over m, to be, epsilon over 2. If each of these could be epsilon over 2, then adding them together would give me the epsilon that I want. So how do I choose capital N? Well, let's choose capital N to be bigger than 2 over epsilon. And that way, if m is bigger than 2 over epsilon, I can kind of imply that 1 over m must be less than epsilon over 2. If n is bigger than 2 over epsilon, same story. I know that this 1 over n should be less than epsilon over 2. Right, so each of these can kind of be bounded by epsilon over 2, and then we get that this sequence has to be a Cauchy sequence. So rather than kind of thinking about the limit, we're kind of thinking about, okay, how do I choose n so that I can kind of bound the an term and the am term in a way that's helpful for us. So it's a bit of a different style, I think, to the proof, but feels very similar to me. Feels a little bit similar. So one lemma before we kind of move into the Cauchy criterion: every Cauchy sequence is bounded. So that's kind of nice. Very similar proof to what we saw earlier. So if I have a Cauchy sequence, eventually I can find a natural number so that I can kind of bound the difference of the terms after capital N by epsilon. Okay, and that should be true for any epsilon that I want. In particular, why don't we just take an easy value of epsilon, like epsilon is equal to 1. So I know that I can bound these terms by 1 eventually for some capital N. And then we can kind of triangle inequality our way into something that's helpful. So we're going to triangle inequality, remove the middleman, I guess. And now we have that am is bounded above by 1 plus this a sub n. Right, so all of my subsequent terms, right, bigger than capital N, should have this kind of upper bound to them. And then the idea is you just want to take the max of all of those first bunch of terms, as well as this one that's going to bound the tail. So my tail is bounded by 1 plus a sub n. And then all we have to do is look at that finite number of dots before we found capital N and see how big they are. And certainly the max of all of those finite number of things should be a bound for the sequence. So you'll notice that this feels very similar to what Dingus did for us last week, right? So every convergent sequence is bounded as well, right? With a very similar kind of argument. All right, so let's prove the last thing that we need to talk about for today, and that is that a sequence converges if and only if it's a Cauchy sequence. If and only if it's a Cauchy sequence. So every convergent sequence is Cauchy, and every Cauchy sequence is convergent. Beautiful, beautiful property to have. So let's do the forwards direction. Let's assume that we have a convergent sequence, right? Specifically, let's just say that a sub n converges to some number. If we look at the usual definition of a sequential limit, that means that there's for every epsilon bigger than 0, I know I can find a capital N that satisfies some stuff. And specifically, I'm going to take capital N in such a way so that the bound of an minus a is less than epsilon over 2. And I can do this because I know it converges. So I can pick really any epsilon value I want. I'm just going to pick epsilon over 2 as my bound. So what we want to show is we want to show that it's a Cauchy sequence. So let's consider the difference of these kind of terms that are in the tail. Okay, let's go ahead and add and subtract a into our equation here. And then we can triangle inequality. So I get that am minus a plus a minus an. That should kind of form an upper bound of this difference of the subsequent terms. Now, I've gone ahead and I've chosen epsilon in a very particular way. I know that this am minus a, because it comes
Prepare
from...
to be iterated.
Oh, thank you for the follow, Nico. So I know that this am minus a has to be bounded by epsilon over 2. Same for this a minus an, right? So both of these an and am are part of this convergent sequence. So I can bound them, I can bound the distance between them and the limit by really whatever I want, any arbitrary number. So I'm choosing epsilon over 2 just to prove that this is going to be Cauchy. Hope you're doing well, Nico. Thank you very much for the follow. So that's the proof of your forwards direction. Now, for the backwards direction, we want to assume that our sequence is Cauchy and show that it converges, which I think is potentially a little bit harder. So we know that a Cauchy sequence is bounded by the lemma that we just proved. Now, what we have now is a sequence that's bounded, so we can use the Bolzano-Weierstrass Theorem and find a convergent subsequence. Okay, so this Cauchy sequence must have a convergent subsequence. Let's call it A sub nk. Okay, this convergent subsequence has to have a limit. We're going to call that limit little a. You're tired, fam. Oh man, it's only like 5. It's only like 5 where you're from. Falling asleep over here. I know, real analysis does that to me too. So there you go. We actually apply our Bolzano-Weierstrass theorem to get this convergent subsequence. Okay. Next, let's kind of unpack the definition a little bit. So the sequence is Cauchy. I must be able to find a capital N where I can kind of bound the difference between the tail terms by whatever epsilon I want. In this case, I'm going to pick epsilon over 2. Okay, so as long as m and n are bigger than this capital N, I should be able to do this because it's a Cauchy sequence. That's the definition. And so I'm going to write this down. So in addition to this, we can choose an n sub k big enough so that these particular terms in the subsequence are arbitrarily close to epsilon over 2 as well. Now I can do that because these particular terms in the subsequence converge. So I know that I can kind of bound them. I can look at the distance between a sub nk and its limit, and I can bound that distance by an arbitrary amount. I'm going to call it epsilon over 2. So now we just have to kind of figure out if we can get a sub n minus a bounded by epsilon. If we can do that, then we know that our sequence converges. So we start with kind of what we want. We're going to introduce a particular ank. So notice this is an n capital K, so I'm going to choose a particular index, and I'm going to introduce that one particular term as a subtraction and an addition. So this is not nk in the case that I'm talking about all of the potential terms in the subsequence. I'm picking a particular one, and I'm saying I know that there's a particular one that I can pick, like there's a capital N that I can pick where I can add this, use the triangle inequality. I have that this must be bounded above by epsilon over 2 because the sequence is Cauchy. And then I have that this must also be bounded above by epsilon over 2 because I know that the distance after this capital N between the limit and that term in the subsequence, I can bound that by whatever I want. So that's kind of the idea here. You're kind of bounding these two pieces that come out of the triangle inequality to get that this Cauchy sequence is convergent. Whew. Yeah, that simple trick of adding and subtracting the same number is so helpful. We did that like so many times in these last couple proofs, right? Like just adding and subtracting, like adding 0. Such a useful trick in analysis, isn't it? So there you go. That's really all the stuff that I wanted to cover today. I'm only 40 minutes over time, which is pretty good for the amount of stuff that we have to cover today. Not too bad. Not too bad. But I need to make a couple of edits to the slide deck. And then we're going to post that slide deck up for you in the Discord server. I don't want to open Discord just in case I'm in a DM. But yeah, that's everything that we wanted to cover for today. Oh my goodness. Oh my goodness. So how are y'all doing? Real analysis would be great white noise. Is it real analysis that's great white noise, fam, or is it just my voice? It might just be my voice. What does my second monitor show? What do you mean? Like this one? This is what my second monitor shows me right now. I got Twitch up over here. I got, sorry, I don't have Twitch. I have Spotify up here, and I have Streamer.bot up here right now. When I was doing the presentation, I had Discord up over there, and I was kind of following Discord chat up in here. But that's usually what my second monitor usually either shows my video game that I'm playing, or it has just a couple of things that I need open. What do I watch on my second monitor while working? Oh, I usually have Twitch open, and I'm usually watching somebody on Twitch. So I have my music running and my streamer bot running over here, and then I'm usually have Twitch open. Or YouTube. Sometimes I'll go over to YouTube and I'll watch like YouTube videos as well. I'm about ready to buy a new rig. I need to buy another desktop, I think, and I'm gonna convert this one into my other work desktop, like my monitoring desktop. So yeah, I might be getting a new setup soon, but I probably won't do that until the spring. But yeah, based on some of the work that I'm doing at the college, I need to... he's always watching. It's true. It's how we find people, right? Like, I can't remember how we found Famish. Did we find you through Twitch, or did you pop in the Discord? But either way, you popped in the Discord, you were talking about some of the streams that you were doing, so I was watching you play Zelda, right? Like, how do we find, like, our cool people that we bring into the elements, right? Like, you found me on Twitch? Yeah. Good luck trying to get those 5 series GPUs. Oh no. Are the chips getting expensive again? But it's how I kind of find people, right? Like so we brought in like Zyphin started streaming, so I was watching Zyphin. We brought in Math Spellbook, right, to the elements, right? And kind of so it's nice to kind of like watch what other people are up to and kind of get their vibe and like. Yeah, I like being able to promote other people that are doing educational content as well. And we have cookies. By cookies, do you mean browser cookies? Or by cookies, do you mean chocolate chip? I don't collect any cookies from anybody. Okay, chat, you're going over here for a hot second. I want to... Oh my god, today was a crazy day, man. Like, we got a new subscriber today. Shoutouts to Peak and Flow for their Tier 1 subscription. Thank you very much for that. Much appreciated. I hope you enjoy your ad-free viewing and access to all of your commands. We had 1, 2, 3, 4, 5, 6, 7, 8 follows today. Damn! So shoutouts to Cookie, Guy across the street, that's creepy, HDD, Luke, T-Double, Joe Pop, WS Ponders, and Nico. Thank you very much for those follows. We're up to 828 followers. We are peaking on 1K, chat. This is getting crazy. And then we had some raid, Jeviqua with a raid of 27 people. Wow, thank you so much for the support. Zach, thank you very much for the bits today as well. Blob as well. Thank you very much for the bits. Fun day, chat. It was you always know how to bring a smile to my face over on Twitch. That's for sure. It was a little quieter. The Discord chat was pretty funny too. They were they were trolling me. It's like, imagine Jeff, but like multiply that by 10. Imagine there's like 10 Jeffs all talking at the same time. That's what the Discord chat's like when I'm doing these streams live. It's hilarious. DS, good to see you. Thanks so much for coming in and saying hi. You're going to work on y'all's brain rot trailer? Yeah, no worries, man. No worries. I'm going to end off stream for the evening. Dawn is on, so we could go raid into Dawn. So I'll set a raid up for us, and that way you got something to watch here. So we'll pop over, we'll say hello to Dawn, and I will bid you adieu because I'm going out for dinner with David and the in-laws tonight. Are you around, Gold? Do you want to jump into a VC after I'm done? I know, it's so nice to see you. Thanks so much, DS. Thank you. When are we back? Let's see. What is today? Today's Saturday. So I probably won't be back streaming until Monday. So Monday, Wednesday, 8 o'clock in Pacific time is when we're doing our linear algebra class, Zach and I. So I actually am leading on Wednesday, so I need to do some work this weekend and start developing a problem set for linear algebra. Oh my god. Otherwise, you might see me over on Talos' stream tomorrow night. So remember, Talos is doing exploratory calculus tomorrow. That usually starts or sometime between 4 and 5, so I might pop in tomorrow and chat with Talos. Otherwise, I'll see you Monday and Wednesday this coming week. Goodbye, everybody. Let's go say hi to Dawn if you need a raid message. There it is. We'll talk to you guys later. Bye-bye now.